Good morning, Dr. Senthil.
Hi, good morning, sir. Good morning, everyone.
Good morning. Good morning, students.
Yeah, good morning, sir.
Morning. Senthil, there are only 15 participants so far. Let's wait for another 2 minutes and then we can start.
Sure, Sudha.
So yes, good morning, guys. So welcome to semester 2. So today, from today, you will be learning what is classification. So it is again a part of supervised learning, where the target variable is a qualitative or a categorical variable. Okay, so for today's session, we will be talking about the basics, whatever is necessary for logistic regression, what's odds ratio. Okay, so all that will be covered today. And over to you, Sindhu.
Yeah, thank you, Sudha. Very good morning to all. So, as Sudha briefed, we are going to jump into the world of classification. So, throughout our last residency, we have discussed a lot of concepts with respect to regression algorithms, how to build the regression model, and how to understand the regression model, and how to do the business interpretation with respect to regression model, right? So, and how to regularize the regression model and all those things. So all of our discussions are with respect to predict something which is continuous in nature. From today onwards, our focus will be on discussing different classification algorithm. While I say classification algorithm. As a part of this residency, as a part of this course, we also going to study some nonlinear regression model, because if you remember, the in our previous residency, the only machine learning model that we have discussed is linear regression. Of course, variants of that we have discussed, like OLS, gradient descent, ridge, lasso, elastic net. But basically, all those algorithms are linear algorithms or linear models. The math that it is using, it's actually a kind of linear equation. But that time itself, at many situation, we have discussed like the R square of the R square value that we got by using the linear regression model is not up to the expectation. The reason is the data relationship, the relationship between the input and the output are not quite linear. So it is more of non-linear. So in this kind of situation, we obviously can't use the linear regression model. So linear regression model or the linear models can useful in terms of understanding the business problem in a clear way, in a detailed way. But in many a situation, prediction is matters. So whenever prediction is matter, I want to predict the output accurately. That is what matters. That interpretation is secondary. So in this kind of situation, we can go with nonlinear model, because nonlinear model have this ability of producing more accurate output. The predictive ability of the nonlinear model will always kind of high compared to the linear model, even though the data relationship is complex. That input output relationship in the data is complex. Still, your nonlinear model somehow finds some kind of relationship between input and output, not by using linear function, but by using different nonlinear function. It able to map the input output relationship. So in that sense, the predictive ability of nonlinear model is always on the higher side compared to the linear model. So in that aspect, most of the classification algorithm and some of the regression algorithm we are going to study in this residency. Majority of the algorithm that we are going to study in this residency is actually nonlinear models. But of course, we are going to start today's session with one linear classification model. So the agenda for today's session is we are going to discuss logistic regression, which is the continuation of our previous residency discussion, which is something about linear regression. So we are going to use the mathematical concept of linear regression. And on top of it, we are going to do few more mathematics or few more modification in that mathematics, so that we are going to build one classification model, right? So throughout today, we are going to discuss only about logistic regression and different performance measures. So as far performance measure, can anyone tell what kind of performance measures we computed for linear regression? What are the measures through which we evaluated our linear regression model?
Accuracy, R square, MSE, RMSE.
That is basically error measures. Error we used to define in different way, like MSE, RMSE, MAPE, so on. And the another measure is, of course, R square, which talks about the explained variance. So these two are the important measures through which we evaluated the performance of the R square. Of course, evaluated the performance of the linear regression model. Of course, we have used some other measures like what is the T statistics p-value for each and every feature, what is the F statistics p-value for the whole model, what is the confidence interval, right? So these are all the kind of other measures that we have used, through which we have commented about the quality of the model. But anyway, at the end of the day, if I want to comment about the model's predictive ability, obviously I have to speak in terms of R square and error in different forms with respect to the linear regression model. Whereas with respect to the classification model, the measures are actually quite different, right? So we can't really compute anything as continuous error. So here we are going to model that error in some other way. So there are some specific measures that we are going to discuss for classification algorithm. That measures that we are going to discuss in our today class, it's kind of common for all the classification algorithm. It is not like logistic regression classification model. We are going to measure with some metrics, and for decision tree or random forest, we are going to use some other metrics. It is not like that. Across all the classification algorithm, only a kind of common measures that we are going to, or common metrics that we are going to use to evaluate its performance. So in our today discussion, we are also going to study all those measures. So in our coming classes, whatever the algorithm that we are going to develop, we will be using this measure to understand the quality of that particular model. So that is the main agenda for today's session, decoding the logistic regression in detail, and how to evaluate different performance measures of classification algorithms. So that is the agenda for today's session. So with this brief intro, let me straight away take you to the board. Let me share my screen. So as I told, the first algorithm that we are going to discuss in today's session is logistic regression. And also I told like logistic regression is a linear model. So as per classification techniques, just a minute. I'm not seeing the chat window in parallel. Just give me 1 minute. Fine. Fine. So the logistic regression that we are going to study in our today's session is basically a linear model. So we already know at what point of time or what under what circumstance I can call one model as a linear model. Can anyone tell? If I'm declaring one model as a linear model, what should be the nature of that model? What should be the characteristics of the model so that I can call that as a linear model?
Residual should be normal.
Sorry?
Residual should be normal.
It should be normal. That is, you are going deep into one particular algorithm and you are talking about residual, all those things. I'm just asking in general.
A linear correlation.
Follow a linear equation.
Yeah. So that basic equation for that machine learning model should be a kind of linear equation. Linear equation in the sense it should have only the arithmetic linear combinations. It should not arithmetic linear combination means plus multiplication, addition, and all those things. But it should not have any kind of non-linear component in it. Non-linear component means it should not have square, it should not have log, it should not have exponential. So while I'm defining that mathematical equation of a model, while I'm deriving that mathematical equation of the model, it should not contain any kind of non-linear term. It should have only the linear term, so that the relationship between the input and output can be easily relatable or directly relatable. So such a kind of equations are linear equation. A machine learning model which is using such a kind of equations are linear models. So we know that for linear regression, the equation is y equal to b1 x1 plus b0. So here you can see a kind of direct linear relationship exists because there is no non-linear term. There is no log term, there is no square term, there is no exponential term or sine term, cosine term, right? So simple arithmetic terms like multiplication and the addition of all those individual term only exist. So obviously this kind of equations are linear equation. So don't confuse linear concept with normality concept. You people told, some of you told like residue should be normal, and also I'm getting one reply like skewness. Of course, these are all the kind of metrics through which we can comment about the normality. But now I'm asking about linearity in general sense, not with respect to linear regression model or any specific machine learning model. In general, in mathematical world, if the relationship between the input and output is not having any kind of nonlinear term, that mathematical equation which is mapping your input and output, it's not containing any any nonlinear term, then obviously it's a kind of linear model. So through which I can easily find or easily capture what is the impact this x1 is creating on y. So that is very quite forward, right? That is throughout for any value of x from minus infinity to plus infinity, the way that y is going to be changed is actually same. It is determined by this b1 and b0, but for that low value of range, it will produce y in this way. For an high value of x, the y will be produced in some other way. No, for any value of x from minus infinity to plus infinity, the way it is actually, the way that x has been converted into y, it is the kind of same. So that is why we are calling this as a linear relationship. That linear relationship is, if you want to exactly trace what is that relationship, you need to know what is b1 and b0. But provided that b1 and b0 for any given value of x, you can directly predict, or you can directly tell this is what the y for the given value of x, provided that this is b1 and this is b0. So such a models are linear models. So linear models always very easily explainable. So now we are telling like logistic regression is a linear model. Now we will decode the concept of logistic regression in terms of its map, and let us see what is the final equation that we are getting. And with respect to that, you can comment on whether the logistic regression model is really a linear model or not. So while seeing this word logistic regression, or the name logistic regression, there are two terms in it. One is regression, the another one is logistic. So the very basic thing that you need to know is why logistic regression is named after the word regression. I told that logistic regression is a classification model. You can't use logistic regression for regression purpose. Regression purpose means logistic regression machine learning model you can't use to predict something which is continuous in nature. Logistic regression can be for binomial. I will come to it. So even if it is multiple categories or exist, you can't really use logistic regression. Of course, using sklearn package, we can use it. But if you see the math of the logistic regression is a machine learning model through which you can predict the output, which is binomial in nature. What I mean by binomial in nature? I'm telling like logistic regression is the machine learning model through which we can predict the output, which is binomial in nature. What is the meaning of that?
There is a two outcome, 0 and 1.
Yes or no, like that?
Yes. Yeah, it should have only two levels, right? So if you are predicting the gender, there will be only two levels, say male and female. If you are predicting the cancerous nature of the tumor, there is only two levels, malignant and benign. So like that, whenever you are in the position to predict this or that, true or false, yes or no. So in these kind of cases, only you can use logistic regression. Of course, we can do some kind of modification in logistic regression so that it can be extendable to multi-class also by again constructing the logistic regression. We will see that concept later. But basically, the math behind the logistic regression will support binomial output only. So obviously, it is a classification algorithm. It is not for predict something which is continuous in nature. So even though it is a classification algorithm, why it is named after the word regression? So that is the main thing that we need to analyze, because once we understand the concept, then it means that we are understanding the whole picture of logistic regression, right? So why it is actually named after regression is, it is the basic math equation that logistic regression using is actually comes from linear regression. The basic fundamental mathematical equation that linear regression, logistic regression using is nothing but our linear regression equation that I have written here. So this is the equation for linear regression. This is the equation for linear regression. Now let me explain how this linear regression equation can be used to construct the logistic regression concept. So whenever I use this equation to predict something, what will be the nature of this y?
Continuous.
Continuous. The y is continuous. So if I apply any value in place of x in this equation, the output that I'm getting is, say, continuous. Say I'm just predicting the salary with respect to experience. Say x1 is an experience and y is an salary, right? So whenever I substitute any experience value in place of x1, like 2-year experience, 2.5 years experience, 3 years experience, 3.6 years experience, whatever it may be, the corresponding output that I'm going to get from my model is some continuous number through which I can define salary. Now the thing is, I want to make this as a classification algorithm. I want to make this basic equation, which is predicting salary, which is actually continuous. I want to modify this mathematical equation so that it's going to do some kind of classification task for me. How can I convert this with respect to domain? Can you tell, rather than predicting the continuous salary information, how can, so this model is now predicting the salary which is continuous in nature. How can I convert this as a kind of classification model? Don't think in terms of math point of view, just tell in terms of domain point of view.
Salary, high, low.
So everyone getting this point? Rather than predicting the salary, what is exact salary? If my objective is like, I want to predict whether the salary is high or low, then it's become a binomial problem, right? Binomial classification problem, right? Is everyone agreeing this? Yes or no?
Yes. Yes.
So that is the kind of outcome that I'm expecting from this equation. Now, as of now, this equation will predict salary which is continuous in nature. Now I'm just going to do some kind of modification so that I'm just going to get the inference like whether for a given input of x1, for the given input for experience, whether the salary is high or the salary is low. That is what I want to predict, so that I can bring this as an, or I can make this as an classification model. So how to do it? How to do it? Mathematically, how to do it, we will see. say if something is continuous in nature, if some output is continuous in nature, what could be the value it can have mathematically?
Anything. Infinity.
What is the extreme values? Can anyone tell?
Minus
It can have
infinity to
anything
plus
from
Infinity, yeah.
minus infinity to plus infinity. It can have any number. Now the idea is, even though salary can be anything from logically, mathematically, it could be anything from some value, say minus infinity to plus infinity. Of course, salary can't be minus infinity, but say any other continuous number. Now, with respect to this example, the salary can be some minimum value to some maximum value. But you may even predict some sensor output. That sensor output can even have minus value to plus value. So in that sense, any continuous number can have any value from minus infinity to plus infinity. Now, my task is, I want to convert this continuous output to discrete. So I'm just going to make use of the probability concept. So I'm going to convert this range from minus infinity to plus infinity to 0 to 1. This is my objective. Whatever the value which is there between minus infinity to plus infinity, I'm just going to convert that as a probability value. So probability value we know, which is only between 0 to 1, right? So how can I do it? Mathematically, how can you do it?
By applying log.
Sorry?
By applying log.
By applying log, do you think always the value will become 0 to 1? Say if you take log for 20, what could be the value? 1 point something, right?
Yes.
No, we can take exponential. I mean,
In divide with sum of all the values.
Exactly. So the two things that we need to do, the point number one is, we have to get rid of the negative. If it say if I want to make this number only between to make this number to have any value between 0 to 1, obviously it should not have any negative value, right? So remove negative effect, right? So this is point number one. So if I do some kind of mathematical transformation and removing the negative effect from this continuous number, now the value can be, after removing this negative effect from my number, the value can be anything from 0 to infinity, right? Yes or no? Obviously my number is not going to have a negative value. My outcome is not going to have a negative value, but it could be any value from 0 to infinity. After applying some transformation to remove the negative effect from my output, even after removing the negative effect, it won't become anything between 0 to 1. It could have any value between 0 to infinity. So after applying this transformation, I have to apply one another transformation, like divide by constant. Let us check what is that constant, or divide by rather than writing constant, divide by number, some max number. So after removing the polarity, or after removing the negative effect, if I divide that number by, say, some maximum value, so here in this case infinity is the maximum value. So if I divide that whole number, all the numbers, by infinity, obviously that value will become 0 to 1, right? Is everyone agreeing this? Performing these two operations can bring your continuous output to something between 0 to 1.
Yes, yeah.
Right? But still it is continuous. I'm not saying that it can have only 0 or 1. I have written as only 0 to 1. But initially the value is between minus infinity to plus infinity. Now, if you do this two transformation, then value now will become between 0 to 1. Now, how to do it? So there are so many ways, as you people are telling, scaling, dividing, there are so many ways to do it. But in logistic regression, the first task has been achieved by taking the exponential. If you want, you can check it out. Even whether you have a positive number in your hand or negative number in your hand, if you take the exponential of it, the result will be only positive. So everyone agreeing that? Whatever the number that you have in your hand, if you take exponential, the result will be only in positive. Yes or no?
Even we convert it into percentage, that would be a 0 to 1, right? I mean,
Percentage?
like in scale of 0 to 100, we can make it 0 to 1 also.
No. I have some input variable which even have negative numbers. Any number, it could have any value from minus infinity to plus infinity, right? But of course, there are so many ways. So even if you can take simple absolute, right? In order to make that as a positive, you can do that kind of transformation also. But here in logistic regression, the transformation that they are using is exponential. So if you take exponential of any negative number, you will get only the positive number as an output. So here that for which negative number we have to take the exponential, or for which value we have to take the exponential?
The least numbers.
Not least number.
The
That is
constant.
this y, because this is what my base equation. Now my objective is converting this y into something between 0 to 1. Yes or no?
Right.
So everyone can follow this. Guys, I'm need a response.
sir.
Yeah.
Yes, sir.
So exponential of y. So in other words, I can even write it as exponential of b1 x1 plus b0. If I take exponential of b1 x1 plus b0, definitely this value will be anything between 0 to infinity. Definitely don't have any negative value for it. Then after doing this, the second transformation that we are going to do is exponential of b1 x1 plus b0. This we are going to divide by 1 plus exponential of b1 x1 plus b0. The same numerator that I'm using in denominator plus 1, so that this value is always between 0 to 1, right? Of course, it won't become exactly as 1 because I'm adding 1 with it, because I don't want to declare anything with the probability as 1. So in the denominator, they are adding 1 plus exponential of b1 x1 plus b0. So definitely this value is now take any number between 0 to 1. So everyone agreeing this?
Yes, sir.
Right. So once you achieved this, this continuous number, which is b1 x1 plus b0, that is an output of your linear regression. Now we have bring down as some probability value between 0 to 1. So now we are going to fix some kind of threshold. So this value, now I can call it as p, probability value. So now if p is anything less than 0.5, then I'm just going to make a comment like it belongs to class 1. Say it is low salary. And if it is greater than 0.5, then it belongs to class 2, some high salary. Right? So why 0.5? Because say with respect to that actual salary value only, we are actually applying this transformation. So we are ending up some value between 0 to 1. So we are just picking up the mid level. So any salary value proportional to the probability value of 0.5 or anything less than 0.5, we are going to consider that as a low salary. Any probability value which is greater than 0.5, we are considering that as an high salary. So now we have converted that continuous output to a discrete. We have converted that continuous output to discrete. So this mathematical, which is an exact mathematical equation which is doing that? Which mathematical equation that you are seeing in board is actually doing that process of converting that continuous output to probability value between 0 to 1?
Second equation.
The second equation. So this second equation is nothing but the equation of logistic regression, right? So logistic regression, converting any continuous output into a probability value using this equation, P equal to exponential of that continuous output divided by 1 plus exponential of that continuous output. Followed by that, it need to apply some kind of threshold logic. Like if the probability is less than 0.5, then it belongs to class 1. If it is greater than 0.5, then it belongs to class 2. So this is how exactly logistic regression works. So this is the reason why it has been named after regression. So even though it is doing a classification task, it is having that regression equation as a part of it, right? Until it is actually computing this in terms of probability. Even if you see that probability equation, this probability equation having that regression equation in it, linear regression equation in it. So that is the reason why logistic regression is named after the word regression. Any doubt on this?
Sir, can you repeat the last sentence once more?
See, so even though it's a classification algorithm, it is named after the word regression. The reason for that is the probability equation of this logistic regression model is having the linear regression part in its mathematical expression. If you see this part is the equation of your linear regression model, right? Again, this part alone is the equation of the linear regression model. So in logistic regression model, linear regression is a kind of internal block. So that is the reason logistic regression is named after the word regression. They are not named this as logistic classification, right? All other models, they have named with that tagline of classification. But here, this model has been named after regression. The reason is, even though it's doing a classification task, it is using the regression equation as a fundamental block in it. Got the point?
Yes.
Sir,
Yeah.
so one question.
Yes.
Sir, why do we have to go through this process? Why can't we have continuous output and then basically select that threshold there and then put them into 1 and 0? If we use simple linear regression and get the continuous output, and then in that continuous output, we select a threshold, and then basically above that is 1, below that is 0. Does that work, or, I mean?
See here, what this probability says, suppose after doing this, say if your probability is coming as, say if you are getting the p-value as 0.3, after applying this equation, say you are getting your p-value as 0.3, what it actually means?
Class 1.
Say there is some 30% evidence, there is a 30% chance that it belongs to class 2. Because we are saying that if probability is greater than 0.5, it is belongs to class 2. Right? If it is less than 0.5, then it belongs to class 1. Now the probability is 0.3. So with respect to the class 1, so for this observation, the chance that it can be a high salary employee is only 30%. So that kind of inference is also very important, right? So if you just like that found some kind of continuous output, and if you are just binning it, it is kind of straightforward application. You can't actually infer anything more. Are you getting my point?
Understood, sir. Yeah. Here it's
Right?
about probability, while there it's just binning and
Yeah, with what confidence that we are telling this is a kind of high salary employee, and with what confidence we are telling that is belongs to low category. Say if it is a cancer, non-cancer patient, with what evidence, with what probability I'm saying that this person can have cancer, with what probability I can say this person not having cancer. So that is also really needed, right? So it is not like he is having cancer or he is not having cancer, he is a high salary employee, he is a low salary employee. It is about to what confidence we are telling that. So that is also important. That can be only possible if you are doing this kind of probability kind of approach, rather than simply of taking the continuous output of the linear regression and just like that binning it with respect to 50 percentile value or 75 percentile value. Right? Now, my question is, this is the p-value that we got. This is the expression that we got. I told that this is the kind of expression for this classification model. Do you think that this expression is a linear one? Do you think that this expression is a linear one?
No, it is sort of S curve.
Okay. So at the end, say z, I'm just keeping z equal to b1 x1 plus b0, and at the end we are getting equation like p to the power e to the power of z, the whole divided by 1 plus e to the power of z. So in place of z, you have to substitute this b1 x1 plus b0, b1 x1 plus b0. So this is the equation that we got now. Now my question is, are you saying that this equation is a linear equation? Is this equation is linear equation or not?
No,
It's not.
Yes.
Not completely
No,
linear.
not linear.
S curve.
Term. So for every change in z, how that p-value change, I can't trace that, because exponential curves are kind of like this. Right here, for 1 unit change in input, there is only small increment in y, whereas here for the same 1 unit increase in input, that increase in output is more. So this gap, it's not actually linear. So obviously that exponential curve or exponential term lead to non-linearity. So obviously this equation is not a linear equation. Then how can I tell that logistic regression is a linear model? With respect to this equation, if I see, logistic regression is actually non-linear model. But we are once again going to do some kind of modification in this equation. Like, say, rather than expression this in terms of p, which is probability, if I express this in terms of p divided by 1 minus p. What is p divided by 1 minus p?
Odd ratio.
Sorry?
Odds ratio.
Odd ratio.
Odd ratio, right? So odd. So what is the chance for something to happen divided by what is the chance that even don't happen? So p divided by 1 minus p. So I'm just defining this or modifying this equation in terms of odds. So if I use this equation, if you solve this, what you will get?
1 over 1 plus e to the power of minus z.
It will get cancelled, no? So e to the power of z, the whole divided by 1 plus e to the power of z, the whole divided by 1 plus e to the power of z minus e to the power of z, the whole divided by 1 plus e to the power of z. This term will get cancelled out. This will get cancelled out, and we will end up with e to the power of z. So everyone agreeing this?
Yes, sir.
So p over 1 minus p, which is equal to e to the power of z, right? So still it is non-linear, right? Still it is non-linear because e to the power of z. So z only is having the input. This I can return like e to the power of p1 plus b0. If I ask what is the relationship between x1 and this probability, which is non-linear, now I am asking the question like what is the relationship between this x1 and the odd? Still it is non-linear. But still one more modification I can do in this equation. I can bring this exponential on this side. If I bring this exponential on this side, what happened?
Log.
Log of.
So this log is a natural logarithm, so I'm just writing as ln. So ln of p divided by 1 minus p, which is equal to z, which is equal to b1 x1 plus b0. Now, what is the relationship between this x1 and the log of odd ratio?
Linear.
I'm not talking with respect to the relation between x1 and probability or x1 to odd ratio. I'm talking about the relationship between the x1 and log of odd. The relationship between x1 and log of odd is now linear, right?
Yeah.
So say consider this ln of p divided by 1 minus p as one variable, say y. Now y and x1 are linearly related, but now y is not just an actual output or any continuous output. Y is nothing but ln of p divided by 1 minus p. What is p? Again, I have to find p using this expression, and I have to take the ln of it. Then I can relate what is the 1 unit change in x1, how it will linearly affect my log of odd. Are you getting my point? For every 1 unit change in x1, previously in our linear regression session, we used to explain like for every 1 unit change in x1, how much y will increase or decrease, how much change will happen in the output y. Here we are actually explaining for every 1 unit increase in x, how much change will happen in log of odd. How much change it will happen in log of odd. In other words, if I take the exponential of b1, rather than expressing like this, say in this expression itself, it's an exponential of b1 x1 plus b0. So rather than explaining b1 effect with respect to the ln of p divided by 1 minus p, for 1 unit increase or decrease in b1, how much increase or decrease will happen in ln of p divided by 1 minus p. This is one way of explaining the model linearly. The other way of explaining the model is I can also take the exponential of b1, because b1 is some constant, right? b1 is some constant. So taking the exponential of that b1, it's going to give one constant only. It's just one number. For that one number, I'm just taking the exponential. So exponential of b1, it's still some constant. Then that constant with respect to 1 unit increase in exponential of b1, what kind of impact it will create in the odd of the output. That is p divided by 1 minus p is odd. So what is 1 unit increase in exponential of b1, how it will affect the odd of your output, that you can explain. So in these two ways you can explain your model. How or what is the 1 unit change in the b1, how it will affect the log of odd, or 1 unit change in exponential of b1, how it will affect the odd. So in these two ways, you can explain your model linearly.
Here both are directly proportional, right?
Yes. That is, b1 is directly proportional to ln of p divided by 1 minus p. In other words, exponential of b1 is directly proportional to p divided by 1 minus p. So in any way you can explain your model to your client to understand the impact of change in one input with respect to the output. While I'm saying b1, this b1 you have to relate with x1. Here this exponential of b1 also you have to relate with x1. So what is the 1 unit increase or decrease in x1? You can explain in terms of ln of p minus ln of p divided by 1 minus p through b1, or 1 unit change in x1 you can explain with respect to p divided by 1 minus p through exponential of b1. Through exponential of b1. Any doubt in this? If of course we are going to execute this. Please let me know if you have any queries. We can explain the relationship between x1 and a ln of p divided by 1 minus p linearly through b1, or we can explain the relationship between x1 and just odd, that is p divided by 1 minus p through exponential of b1. So that is the reason why it is actually known as linear model. So linear model with respect to explaining the model in terms of odd ratio or log of odd ratio. Got the point, everyone?
So examples, like based on this, how we can interpret, let's say if we take some examples.
Okay, say x1 is age, right? So x1 is age, and say I'm getting the b1 value after doing algo calculation. I'm just getting the b1 value as 2.1, right? And I'm just predicting the cancer nature. Cancer nature. That is what my cancerous nature is my target. Now, how can I explain my model is, for every 1 unit increase in age, the odd of getting the cancer will increase by exponential of 2.1 times. Are you following my statement? The for every 1 unit increase in age, the odd of getting cancer will increase by exponential of 2.1 times. Exponential of 2.1, if you calculate, exponential of 2.1 calculate, say if you are getting, I'm not sure about the value, say if you are getting 4.2, then you can tell like for every 1 unit increase in age, the odd of getting cancer is increased by 4.2 times.
Yeah.
What will happen if it is categorical?
If it is categorical, say male, right? The input is male, the another level is female. So male could be represented with 1 and female is 0. So with respect to that absent, you have to explain, provided that your dummy encoded it, then you have to explain like, say for this also the coefficient is say is the same 4.2. How can you explain the odd of getting the cancer for male is 4.2 times more than female?
Okay.
Everyone getting this point? Of course, we are going to do this with respect to one data set also. But anyway, please let me know if you have any questions.
So here the 4.2, we again make a grouping by yes or no, or 0 or 1.
I'm not getting your question.
So so like previous sheet, we said if p is less than 0.5, then mark it as class 1. So something like that. We further make it as
no. See, I understood your question. Say like previously I told no. So anyway, for predicting the output, mission is not going to use this log of odd and all. Log of odd p divided by 1 minus p, nothing mission will compute in order to tell whether the person is having cancer or not. In order to tell whether the person is having cancer or not, only p is required. Once you have p, if p is greater than 0.5, we are going to declare that patient is the cancer patient. If p is less than 0.5, we are going to declare that patient is non-cancerous patient. This workout that we did for explaining your model. For explainability only this part. Say if you want to explain what is the impact of one input feature on the output, what is the impact on age on getting cancer, what is the impact of gender to getting the cancer, what is the impact of smoking habit to get the cancer, that explanation we need to do. No, that explanation I can't do with this expression, because here also x is there, here also x is there. If I expand this z, it will become like b1 x1 plus b naught. If I expand this z, it also become b1 x1 plus b naught. So I can't just explain what is the increase in the probability if x is changed by 1 unit, because this relationship is highly nonlinear. So I'm just decoding this expression in terms of odd and log of odd. Once I decoded this equation or transformed this equation in terms of odd and log of odd, we are getting a direct relationship like this. Then with respect to this equation, I can explain like for every 1 unit increase in x1, the odd of getting hard disease is increase or decrease by b1 times. For that explanation, we need to, for explaining that model, this part will be useful. For predicting the model, for predicting the output, this part is not at all needed. For predicting the output, just P is enough.
Okay.
Got the point?
Yes.
Any other queries?
Sir, one term I didn't recognize. What is H in that formula?
What is
H? There is a term H there in the like left side.
No, this is not H. This is 1 plus.
1 plus c square.
Okay.
E to the power of z. So I told no, e to the power of say here e to the power of z divided by 1 plus e to the power of z is p. P divided by 1 minus p. I'm computing. So
yeah, I got it.
See, this is very important concept. Why I'm keep on asking whether you understood this, because even in coming days, if you are studying anything with respect to the neural network base equation is this one. So logistic regression using the base equation base equation as linear equation, whereas for neural network the base equation is your logistic model. So if you just put one activation function at the output of your this equation, it just become a kind of neural network model. So logistic regression is the basic equation for neural network models too. So this is how exactly that logistic regression works. Now you might understood like why this algorithm is named after regression and what is the meaning of that logistic. What is the meaning of that logistic? So I have explained all those things. Say this part is there, no? You people told p divided by 1 minus p as odd. Log of p divided by 1 minus p, people will call it as logit. This ln of p divided by 1 minus p, people will call it as logit function. So that is the reason why it is known as logistic regression. Logistic regression. Children got this?
Sir, one question here. In the below line, x1 of b is equal to ln of p by p 1 minus p. Are we assuming b naught is 0? I didn't understand this line, the x1 line clearly.
No. See, whenever you are explaining the model to your client, you will explain with respect to only one variable at a time, right?
Okay.
You remember in linear regression, even if you have multiple variables like y equal to b1 x1 plus b2 x2 plus b3 x3 plus b naught, in what way we will explain the impact of x1 on the output y? We will explain like 1 unit change in x1 will affect y by b1 times, keeping all other inputs are constant.
Yeah, correct.
Right. So which
Right.
means that the impact of x1 we are actually modeling with respect to y using only this b1. That is what here also I have written. If you want to do the prediction with the same model, if you want to do the prediction, of course all the x's need to be applied and it need to be multiplied with b1 and also it need to be added with b naught. Then only the actual output you will get. But now we are talking about the explainability. What is the impact of this one particular feature on the output? In that sense, if in order to explain what is the impact of this x1 on this log of odd or odd, you have to explain that with only b1 or exponential b1.
Okay, understood, sir. So this is not a further equation. This is just explanation of the previous step. Understood.
Yes, it's an explain how I can relate the input to the output. What is the impact of each and every input it is creating on my model output? For that, we are just bringing this into odd, log of odd, and all those things in order to just make the prediction whether it's a cancer or non-cancer, whether it's an high salary or low salary. We no need these kind of equation at all. Just this P equation itself will predict whether it is belongs to class 1 or class 2. Once you predict it belongs to class 1 or class 2, you need to understand what is the input feature which actually made your algorithm to make the decision that it belongs to class 1. In order to understand that, you need to see this B1 coefficient, and you have to relate that X1 log of odd or odd relationship through that coefficients.
Okay, sir. Got it. Thank you.
Yes. Right. So this is the reason why it is actually known as logistic regression. Now what we can do is, I'm just taking you to Jupyter Notebook, which with one basic dummy data first, and we will try to raw code it, right? So without using any function from Python, as we used to do for linear regression also. Here too, we will just implement the logistic regression using all the mathematical equation that we have discussed. So just open one Jupyter Notebook. So just import only these two libraries, and later on, whatever the library that we want, we can include. Let me just give you one data frame, a simple data frame. Also, I'm just pasting this in chat window so that you can directly use it. So I'm just creating one simple data frame, which is having two information like weight and hard disease. So it is like based upon weight, I'm just predicting the hard disease, right? So a simple dummy equation in order dummy data set or toy data set through which we can understand the math flow of logistic regression. So for that, I have just considered only one input column, which is nothing but weight, and the output column is hard disease. Of course, that output column hard disease is binomial in nature. It is having two levels, 0 and 1. Now, do you have any, so can you quickly plot it? So from matplotlib, import pyplot as plot and import cbon as sp. So I may require these two. So I just imported, and I'm just simply plotting this with scatter. So plot.scatter of data of W, which is nothing but my weight column, comma data of HD, which is nothing but my hard disease. Of course, I'm just giving some color, C equal to data of HD, because as I'm having two levels here, one is for hard disease yes and hard disease no. Hard disease have two levels, 1 and 0. So all the hard disease observations which with 1 has been represented with blue color, and with sorry, all the hard disease with 1 has been represented with yellow color, and all the hard disease all the observation with hard disease 0 has been represented with blue color, right? So this is the kind of distribution of this simple toy data set that we are having. Now, as I told, the basic equation for logistic regression is a linear regression. So try to fit the linear regression on this data. So generally, when we apply linear regression, we have a kind of linear trend between the input and output, and we will fit a kind of balanced line for the data. But here we can see, as the output is discrete, we can't get that kind of linear trend throughout. At 0 level, we have some samples. At 1 level, we have some samples, because the output can have only 0 or 1, right? So with respect to classification, we will get this kind of distribution only always. Now, try to fit these data points through a linear regression line. Through a linear regression line. Can anyone tell how can I find the B0 and B1? I'm just simply keeping X equal to data of W and Y equal to data of HD, that is input and output. Can anyone tell how can I compute B1 and B0? Anyone remember the formula for B1?
Log of odds.
No. Linear regression B1. So here I'm not talking about, see, don't confuse with this. I'm not talking about this B1, right? So I'm talking about the B1, that is the coefficient which is exist in the expression of this Z. Z is the linear regression output. So the linear regression output is having coefficient B1. How can we just compute that coefficient? Even just in a OLS way. Of course, here we are not going to use OLS, but anyway, first I will explain with the things that we know. Then I will go into log likelihood and all those things. Anyone remember how we will compute this B1?
Sigma x minus x bar into y minus y bar by sigma x minus x bar whole square.
Exactly. So x minus x dot mean
Y minus y.
x dot mean into. So I'm just putting this whole thing in one bracket. X minus x dot mean into y minus y dot mean. The whole thing we have to sum it up, right? NP dot sum. The whole divided by, what is the denominator? X minus x dot mean square. So again, I have to do NP dot sum of this whole denominator, right? So just see in our previous session notebook, we have implemented this. So we also saw the proof for this formula by taking how to apply OLS and find that rate of change of that cost function and all those things actually lead to this formula B1 equal to x minus x mean into y minus y mean whole divided by x minus x mean the whole square. So if I execute this, I'm getting the B1 value as 0.289. So every one of you getting this? I just copy pasted this. And similarly, we can find the value for B0 for the linear regression. That is intercept y dot mean of, that is y bar minus minus B1 into x0. So I'm just computing B0. So B1 we are getting as 0.02 and B1 we are getting as B1 we are getting as 0.02 and B0 we are getting as minus 1.66. So just find the Y-reg, that is the regression output, continuous regression output using these two values. So B1 into X plus B0. B1 into X plus B0, which is nothing but your Y-reg. So this is from that place only we have started, no? Is that equal to B1 into X1 plus B0. So now in this workout, I have just kept that as Y-reg. So Y-reg is B1 X plus B0, which is continuous linear regression output. So just plot this. Just plot this. I just copying the same thing. Here itself I am plotting plt dot plot of x comma Y-reg and plt dot plot of Okay, let me first plot this alone and see. Is everyone agreeing this? This is a kind of balanced line which is fitting this point. Everyone got this? Yes or no?
Yes, sir. Yes, sir.
So obviously there is no meaning in modeling this kind of classification data with this line, right? If you compute the error, it is having lot of error, right? Each and every point, the deviation with respect to this line is actually more, right? So that is the reason we are applying that kind of transformations, right? And in order to make this continuous output, this line is continuous. This line is continuous because I have plotted this line with respect to the linear regression output y rate. So it is continuous in nature. But I want to make this as a kind of classified output. So for that, I'm just modeling this line in terms of probability. So if you want to model this line in terms of probability, what you need to do? This is y rate. Y rate is having some negative value, some value more than 1, right? If I want to bring this into probability, what I need to do? I need to bring all those numbers between 0 to 1. For that, what I need to do?
We have take the exponential now.
Exponential.
Right? So is this equation is correct? P equal to NP dot exponential of y rate the whole divided by 1 plus NP dot exponential of y rate. Are you agreeing this? This is the same equation, right? E to the power of z, 1 plus e to the power of z. The z only I have kept it as y rate, so that now I'm just getting the probability. Just print this. Now you can see all the values. Now you can see all the values between 0 to 1, right? So there are so many ways to achieve the threshold. How to achieve the threshold? SK alone is going to use the threshold of 0.5, but it is actually doing it in a proper way by applying a lot of solvers. Now we have just used the OLS solver. Obviously, for logistic regression, we can't use OLS solver. Here, if you see, how can I compute that coefficient? B0 and B1, I have used the OLS equation because as of now, that is the equation that we know to find the coefficient of linear regression. But anyway, here we are using doing logistic regression. So we have to compute this B0 and B1 using some other mathematics. But I will take you to that. But as of now, with respect to computing this B0 and B1 using the OLS strategy, I have ended up with this probability. Now, with respect to this probability, I'm going to form some threshold. So the threshold, rather than taking the simple 0.5, I'm just taking the threshold as the mean probability. This is the kind of probability for each and every observation, for each and every weight. It actually tells, say, how can you infer this first number 0.53 with respect to that initial toy data that we are having? How will you infer?
53%.
53% chance.
53% for that person. Can you tell what is the weight of that person? The first person weight is 62. A person with the weight 62 can have the chance that he can have odd disease is 53. The percentage chance for a person with a weight 62 can have odd disease is 53. 50% chance is there that person with weight 62 can have odd disease. So the probability is less here in this case, 0.48. So he has only 48% of chance to get the heart disease. That is what this p value is telling to us. This is the probability of that particular observation to belongs to that class 1 or to belongs to your target class. Here the target class is the level for which we are having the value as 1, right? So say if you want to define this probability with respect to not having odd dices, what you need to do? Here I'm just defining this
1 minus.
probability as what is the chance that he is having the odd dices. If you want to define this in terms of not having the odd dices, in your original data you have to change all the ones into zeros and zeros into ones. In that case, say if you are defining all non-hard disease cases as 1 and all the hard disease cases as 0, then while you are giving your explanation with respect to this probability, you have to speak this, or you have to infer this probability value in terms of not having odd disease. Are you getting my point, everyone?
Yes.
Sir, no?
Yes.
Yes, sir.
Right?
No,
So,
sir. No, sir. Could you please repeat?
see, the meaning of 0.53 here is that what is the chance that one particular person is having odd disease? Why I'm making that statement? Because in my data set, whatever which is mentioned as 1 is having odd disease. Whenever a value is as 0, then it means that that particular person is not having odd disease. So 0 is the level indicating not having odd disease. 1 is the level which is indicating the person who is having odd disease. So with respect to that, I can infer this probability. As a person who this first person chance to have the odd disease is 53%. Now suppose in your original data set, you are encoded like whenever the person is having odd disease, you are mentioning that as 0, and whenever a person is not having the odd disease, you are mentioning that as 1. Then you have to infer this probability. As this is the chance that particular person is not having odd disease. Got the point?
Sir, in this case, model always take 1 in consideration.
See, this p-value, it is actually with respect to the level that you have marked as 1.
Yeah.
Encoding
So,
system only do that, right?
if I have 1 and 2, then?
No. I told no, it's a binomial. Only 2 levels.
Yeah, the 1 and 2 is also binomial, right?
Yeah, 1 and 2 is binomial, but while you are giving with respect to the logistic regression, you have to give it as 0 and 1. Then only that convergence, everything will happen properly.
Okay.
This is an exact reason why I have told your logistic regression is for only binomial. If it is more than 3 level, if more than 2 level, how it will work? It will work, but in some other way. This concept directly you can't apply. Are you getting my point?
Yeah. No, so basically I was saying I'll have a binomial only, but level will be 1 and 2, maybe 1 and 5.
No, that's what I'm telling. No, 1 and 5, 1 and 2, even if it is there internally while it's doing it, one level it will make it as 0, another level it will make it as 1. Then only that probability inference you can bring in.
Yeah. Okay.
Right? So this is the exact reason why your logistic regression can't work for multiple classes. Of course, multinomial concept is there separately. For that, we have to do some extra things with this max so that we can extend this to multi-class also. But basically, whatever the one class, this probability is directly inferring that one class chance. And if you want to infer this probability with respect to the 0 class, one thing is you have to invert this 1 minus 0.53. Otherwise, in your data set, you have to invert all the ones into zeros and zeros into 1. Everyone got this point? I think someone of you asked me to explain this. You got this point?
Got it, sir. Thank you.
So now I'm just keeping the threshold of this probability, the average of this probability as a threshold. So if you see this TH value, we are getting is 0.616. So the kind of idea is whenever the probability value is greater than 0.616, I'm just going to make a decision like that person is having odd disease. Whenever the threshold value, whenever the probability value is less than this threshold of 0.61, I'm going to make the decision like the person is not having odd disease, right? So for that, anyway, in future, I may require this thing. So I'm just copying this because I'm going to change those threshold values or that probability values. So if I once again required the initial probability, I have to run all those things once again. So I'm just copying it. And I'm just going to do something like P1 is greater than or equal to TH. I'm just changing all the P1 positions in which P1 is having the value greater than or equal to TH as 1. Similarly, if P1 is having any value less than the threshold, I'm just making that as 0. Now if you see P1, the P1 is now just 1 and 0. Now the P1 is now 1 and 0. With respect to that, the observation number 0, observation number 1, observation number 2, and observation number 5 are predicted as non-odd disease, no odd disease, and observation 3, 4, 6, and 7 has been predicted as odd disease. Has been predicted as odd disease. Everyone getting this point? Any doubt in this? Zoom the screen. Let me zoom it.
Why we are taking threshold as mean? Why can't we take 70% or 75%?
Yeah. So that is the agenda of today's session 2. So we are going to actually explore the model for different thresholds. What happened? How my model performance differ for the different thresholds, starting from say some lowest threshold to threshold 0.2 to highest threshold 0.9. So that we are going to explore. What is the kind of impact that it will create in my model if I fluctuate the threshold? For example, say you are doing the cancer prediction. So or you go with the mean threshold, say, or you go with the mid threshold of 0.5, or even you go with the threshold of 0.3. I'm getting one question, sir. What if P1 equal to TH? It's 1. No, here I have written, right? Greater than or equal to TH. Exact boundary. I'm just allotting that as class 1. Of course, with the 50% evidence only, we are declaring that. It's a mid. We can't tell that in a confident way. With the 61% probability, we are telling that it belongs to class 1. If some probability which is slightly less than that, say if it is 0.6, even with 0.6 probability, we are telling that as class 0. But if it is having any probability equal to or more than 0.61, we are actually telling that as class 1. So that is actually the advantage of modeling through this probability value, because to what extent, with what confidence we are making the decision, that also we can get, rather than just saying that it is class 1 or class 2. With what confidence, with what probability we are telling that it is class 1, and with what probability we are telling this is class 0. That inference also we are getting here.
This is only 50%, right? 50% confidence.
Not 50% confidence. And now here it is 60 with 61%. The probability here I am not keeping the mid value as a threshold. But anyway, in sklearn, if you do without OLS proper mathematics that I am going to discuss, if you use, then generally that sklearn is using the mid value. But here I am not using the mid value. Can you see that?
You are taking mean, right?
What is
threshold? No, you are taking mean as a threshold.
Yeah, of course, mean as a threshold, but mean is not actually exactly lie in the mid of that probability scale. Probability scale is between 0 to 1. Now I'm not getting the threshold as 0.5, right?
Mean is, that means the mean means the 50%, right? Average. Mean is the average. That's 50% confident. 50% confident. 61% is the odd disease person.
Yes, so with the 61% confidence, we are telling that say if someone is having exactly, that is for one guy, this equal to condition is getting satisfied, then the inferences with 61.6% confidence, we are telling that this person can have heart disease.
Confidence, we are telling 61% is the
threshold.
Is the heart disease person. Is that wrong?
I think who is speaking, whether I am hearing like that or everyone is
I think
hearing is what?
it's for everyone.
Yeah, we are getting
We are getting same thing.
Raghavendra,
Others
please
also.
put it in the chat window. There's a lot of disturbance in your end.
Sir, I have question. So the logistic regression is impacted by outliers?
Logistic regression, of course, it have an impact with respect to outliers that we will going to discuss. Say with respect to the kind of math that I have discussed as of now, it is actually not having the impact with respect to the outliers, right? But the thing is, the way that it is computing this B0 and B1, now I have just demonstrated with the OLS. But if you see, it is using some kind of optimization techniques. So that optimization techniques like maximum likelihood estimation. So maximum likelihood estimation is one probability technique through which if you are computing this coefficient, then that technique is sensible to the outliers. But if you are using other techniques like gradient descent or some kind of stacked solver to compute those coefficient, then you don't need to much worry about the outliers.
Okay. And sir, another question. So is there any theory like those who are nearby to boundary threshold points, we can put those as a doubtful, like we're not sure whether they can be 1 or 0?
Yeah, exactly. So that is the reason why we are not only focusing on what is the level, we are also focusing on with what probability that level has been assigned. So that with respect to the domain, you have to make the decision. Say, for example, in my objective is to predict the cancerous nature of the patient. So that time, even I will reduce this threshold, right? Say I won't go with mean threshold, or even I won't go with the mid threshold of 0.5 for the probability scale of 0 to 1. I will even go with the threshold of 0.3 because that decision that I'm going to make is very critical decision. I don't want to take any risk. So my idea is, even if there is a 30% evidence that, or even there is a 30% symptom or evidence that that person can have cancer, I will declare that this person can have cancer, because I don't want to take a risk of increasing the threshold to 0.5, and only if that particular person is having any probability value more than 0.5, if I am declaring him as a cancerous patient, it's too risky, right? So on the other hand, you are doing some kind of analysis where you want to predict the salary, you want to predict the age. That time, even you can increase your threshold a little bit up, because the kind of decision that you are going to take is not really very much sensitive. Then in that case, even you can go up, you can increase the threshold a little bit up. Whereas the kind of life-saving decision that you are going to take through your machine learning model, in that kind of scenario, even you can reduce your threshold. So even if 30% symptom is there, you are going to declare that that person is having COVID. You are not going to wait and you are not going to see for 50% chance. Even if 30% symptoms are there, we are going to declare that person may have COVID. So you need to isolate himself. So that is the kind of idea to play with this threshold. In today's session itself, we are going to play with this threshold. Only after discussing all the metrics, how that each and every metrics will get affected by varying this threshold between 0 to 1, that we are going to discuss in today's session.
Sir, is this the only way we will calculate the threshold?
No, as I told, no. So in sklearn package, always the threshold is 0.5, right? Irrespective of whatever the data set that you are applying, the threshold is only 0.5. But we are going to explore the model with respect to the different threshold. And this is a kind of hyperparameter. Did you remember for Lasso and Ridge and all, we have chosen for what alpha my performance is better, right?
Correct.
So similarly, we are going to vary this threshold also with respect to that domain expectation, with respect to that domain, or with respect to what kind of output that I require, I will play with this threshold, and for which threshold I'm getting the result that I'm looking for, that threshold I will keep the final threshold for my model. That is the idea.
Why? Because sir, in this problem only we are considering heart patients and heart disease, not patients not having heart disease, right? So if we collect healthy patients more, the probability value, this threshold value will become less, right? If we consider
but anyway, average, yeah, of course. Say here with respect to this, I'm just telling how the threshold has been applied, and it is actually dividing your classes. As I told, this probability value itself, we are getting through this OLS mathematics. Obviously, logistic regression at the end of the day, it's not going to use the OLS mathematics. So it has used the mathematics in such a way, like that balanced position of 0.5 is it's reasonably applicable for all the data set.
Okay, sure.
Right. So don't worry about how here say how I'm taking the mean. So if the high towards 1 there is so many probabilities are there, then obviously this mean will go upward. So of course it will go like that, but still this is going like that because of the kind of math that we are using here. Just for the demonstration purpose, I'm just using the math of OLS, but really speaking, it will use some other math that we are going to briefly discuss in today's session itself.
Sure.
So once I have decided this threshold, and I'm using the threshold, I'm making this output as a discrete one. Even I can plot this now. So I can connect all those ones and zeros. For that, what I'm doing is, let me use this same code. Plot dot. I'm just sorting it because that x-axis, comma, np dot sort of p1. Can you see? Now you see that p that we got is from the equation e to the power of z divided by 1 plus e to the power of z. So once I got the probability, I just connected all those probability points. So all the 0 points and all the 1 point simply I have connected. You can see some kind of S curve, right? Yes or no? So even though it is not a very smooth S curve, basically we have seen this equation, no? So if you plot this equation, e to the power of z divided by 1 plus e to the power of z, this equation, people will call it as sigmoidal curve or S curve. This equation, people will call it as sigmoidal curve or S curve, which actually transform your continuous input to the probability level. So we have proven that mathematically, but this is the kind of graphical explanation. If you plot this curve, for any value of x, always you will get a curve like this. A curve like this. So this curve, people will call it as a sigmoidal curve or S curve. So obviously, if you have any input, let me draw this in a new. See, we have e to the power of z divided by 1 plus e to the power of z. If you plot this, you will always get a curve like this. You will always get a curve like this. So this curve is known as sigmoidal curve. The slope of the sigmoidal curve. slope means say I can draw a curve like this, or I can draw a curve like this, or I can draw a curve like this, right? So all those curves are sigmoidal with a different slope, So people can also model this like 1 divided by 1 plus e to the power of minus z. You think these two equations are same or different? E to the power of z divided by 1 plus e to the power of z. I can also write 1 divided by 1 plus e to the power of minus z. Yes or no?
Yes.
So if I do this, numerator and denominator, if I divide by e to the power of z, I will get this equation. No, so basically the equation for this curves can also be written as 1 divided by e to the power 1 plus e to the power of minus z. So 1 divided by 1 plus e to the power of minus b1 x1 minus b0. So by changing b1 and b0, you can come up with a different shape. It is like a kind of rubber band. You can stretch it in any way that you want by adjusting this b0 and b1. So you have to sketch that in a way so that it become a correct mapping function for your input and output. Say for example, say this is the output y, and say this is the input x. Say I'm just fitting this through this sigmoidal curve. Say this is your weight, and say this is your hard disk. Say the weight is, say here 40, 50, 60, 70, 80, 90, 100. 90, 100. Now, what this sigmoidal curve is doing is, say if one person weight is 50, the corresponding value on this probability scale, say this sigmoidal curve will convert this any given input into probability, because we already see this, right? So this equation is equal to P. This equation is equal to P. So whenever you substitute one value here in place of Z is again in terms of B0, B1 and X1. So if you substitute any value for X, then obviously that output you will get is probability. Say here the probability is 0.2. And say for 0.7 or 70 kg, the probability is 0.65. For 80 kg, say the probability is 0.95. And for 90, say the probability is 0.99. So which means this function is actually mapping your input or converting your input to proportional probability values. So with a person with 50 kg of weight will have only 20% chance to get the hard disease. A person with 70 kg of weight will have 0.65 65% chance of getting hard disease. A person with 80 kg will have 90% chance to get the hard disease. A person with 90 kg will have a chance of 99% to get the hard disease. Right? So this is what we have already discussed, but we have discussed in terms of just equations and executing that equations in Python. But if you plot that equation, if you plot this equation, you will get a curve like this. This curve is known as sigmoidal curve. Understood?
So, and this curve is symmetric, right?
This curve is symmetric.
Yeah.
Of course, it is actually a kind of symmetric curve, but really we no need to go into that whether it is following the symmetric characteristics or all those things. This curve slope has been getting adjusted. Say if the scale is like this, say sometime at very higher value only the class is 1, and for the low value only the class is 0. Then the shape will be like this. The shape of the sigmoidal will be like this. It should be a too much of stretched one, and it will come like this, right? Because for the very high value only, the level is going to become 1. For low value, the level is become 0. In between, there is no defined sample in your data set. Then that room in between, the room is more between the class 0 and class 1. Then that the shape of that sigma model is too much of stretched one, something like that. So of course, in all the cases, it look like a symmetric curve only. In front, this style and this style should be a kind of having equal length for that whole scale of your input. But anyway, we are not going to do any kind of inference by seeing that symmetry of this curve. So my point is, whatever that equation that we have derived and we have just executed, if you plot it, you will get a sigmoidal curve. Any doubt in this? Guys, are you there?
Yes, sir.
Yes, sir.
Stories.
Yes, sir.
Yeah.
Yes, sir.
Fine. Now, the next concept that we need to discuss is, I told like it is actually using different math to find those coefficients. Can anyone tell how we used to find those coefficient in linear regression? That B0, B1, all those things. How we used to find in linear regression?
Gradient descent.
Gradient descent or OLS. So whether it's a gradient descent or OLS, what is the base equation from which we applied some math to find those coefficients? What is the base math? We have started.
Y minus.
It's slope equation.
What is an objective function? Say in other words, if I ask what is the objective function for linear regression, what is your answer?
Minimizing
Sum of
error.
y minus y naught.
MSc or
It's a root mean square error.
Yeah,
Y
the
minus y naught whole square.
exactly. So that MSc equation, we have like
Sigma.
summation y minus y cap the whole square, of course, summation the whole divided by n. If it is only SSC, then only y minus y cap the whole square. So this is the starting point. This is a starting point from where we have just applied all our gradient descent or OLS, whatever different algorithms through which we have computed our coefficients B0, B1, so on up to Bn. But here we can't use this equation. Here we can't use this equation because say we at the end we have the model. We have expressed our model in terms of log of odd, which is nothing but, or log of odd or odd, which is nothing but p divided by 1 minus p, right? So if p equal to 0, what happened to this odd? And if p equal to 1, what happened to this odd?
P equal to
Infinity.
So if p equal to 0, then odd will become 0. If p equal to 1,
odd becomes
then
infinity.
odd becomes
Infinite. Undefined.
Even if you take log of odd, log of 0 is not defined, right?
Yeah,
So no.
undefined.
Right, so you can't define. You can't define the log of 0 or ln of 0. Of course, log of infinity, that is also a kind of undefined thing. So that is the reason why actually we can't use MSc, because if you see in terms of odd, for a probability between 0 to 1, the odd ratio can have the value between 0 to infinity. For the probability between 0 to 1, the odd ratio can have the value to 0 to infinity. So our objective function is something like bringing some value which is close to infinity to 0, because we have to minimize it. We have to minimize the deviation. And up to infinity, it could have some kind of very high value. So bringing that high value to some kind of minimized value, it is not mathematically a kind of feasible thing to do with. So basically, this kind of cost function people won't use. So we won't use this kind of cost function for logistic regression. So this is the cost function or loss function we have used for linear regression. This we are not going to use here, because we have to ultimately at the end we have to do the model interpretation, everything with respect to the odd. So if I just see the odd scale for a probability 0 to 1, the odd could have a value between 0 to infinity. So bringing down some deviation from some value close to infinity to any value close to 0 is a kind of uphill task. So obviously we are not actually going to use this concept of use this equation for loss function. So here we are going to use that loss function concept in a different sense. So in what way we are going to use it? Say for example, let me see like actual output. Right? So actual output under this probability. Actual output under this probability. Say I'm predicting something for which the actual output is say 1, 1, 0, 1, 0, 0. And my model is giving the probability as 0.8 or 0.9, 0.7, 0.2, 0.3, 0.6, and 0.1. Right? So this is the actual output. In my data, the output levels are like first 2 observation, the level is 1. That for the third observation, the level is 0. For the fourth observation, again level is 1. For the fifth and sixth observation, the level is 0. So my model is actually predicting the 0.9. For the second observation, the value is 0.7. For the third, 0.2. For the fourth, 0.3. For the fifth, 0.6. For the sixth, 0.1. So can you comment about the quality of the prediction? Take this first observation.
That's correct.
For this first observation, what do you feel about the quality of this prediction? Whether it's a good prediction or not?
It is a good prediction.
It's correct.
Good prediction.
Whether it's a good prediction or not?
Yes, a good prediction.
Good prediction.
So how you are saying this is a good prediction?
With probability.
Probability is high.
How you are saying this is a good prediction?
Because
So the probability is
90%
high.
probability.
So actually the actual output is 1, and with 90% probability, my model is telling that it belongs to class 1. So
Yes.
it's a good. What about this?
Is a good.
So I can say this is a kind of good prediction. This is moderately good, right?
Yes.
It's not very good, right? So with 70% probability, it's telling that it is 1, but still there is a 30% doubt or 30% suspectness is there that it may belong to class 0. What about this?
Good.
Good.
It is good.
Whether it's a good prediction or bad?
Good.
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 So it is once again good, right? Because the actual value is 0, my model is predicting this as 0.2. So obviously it is a good prediction with only 20% probability. It is telling that it is belongs to class 1. Say that is why I have insisted on the point before. The probability values you have to relate to with the level of 1. So here the 0.2 probability means 20% chance is there that it belongs to class 1, which means 80% probability is there it belongs to class 0. So with respect to class 0, it is actually that actual value is 0, and with 80% probability it is telling that it belongs to class 0. So it is a kind of good. Whereas this one,
Bad.
this one
Bad.
is bad. So this one
Bad.
is
Moderate.
also kind of bad. Kind of bad, because only 40% evidence it belongs to 0, because 0.6 means 60% evidence it belongs to class 1. But if you see the actual output, it's 0. Similarly for this,
Good.
good. So we are going to use this concept to model the loss function for the classifier, for the logical regression classifier. Now the idea is the product of, for a very good prediction, the product of all this probability should be very high, right? Yes or no? So for example, I'm calculating something like this. For the first thing, the goodness I can measure as. Someone need to mute yourself.
Abhishek.
Right. So for that first observation, I can consider 0.9 as the measure of quality of that prediction. Then for the second observation, I can use this 0.7 as a measure to define the quality of the prediction. For the third observation, can I use the 0.2 as a measure to define the quality of that prediction?
Yes.
So if I ask what is the quality of this prediction in terms of some number, can you tell it is 0.2?
No, it's around
No.
It's 0.8.
0.8 or 0.9.
0.8%.
So with a 50% chance, it is telling that it belongs to 0, and actual value is from 1. So 1 minus 0.2 is the quality of that particular observation. Then what about the next sample?
It's 0.3 only.
The next sample is 1. So it is 0.3 only.
0.3 only, yes.
I can't simply substitute this as from 1 by saying that it is less than 0.5, something like that. The actual value is 1, but my model is telling that it belongs to 1 with only the probability of 0.3. The chance that this particular observation belongs to 1 is only by 30%, but that actual value is 1. So the quality of the prediction is kind of poor. So I'm just keeping that as it is to mention that. Then what about the next one?
So sir, here third row is I think will be bad, right? For prediction 0, if 0.2 is be bad.
No, okay. This that is what I told. This values you have to relate or you have to infer with respect to class 1. The probability is telling like to what is the percentage that it belongs to class 1. So here this 0.2, how you can infer this 0.2? There is only 20%. There is a 20% chance that it belongs to class 1, which means 80% chance is that it belongs to class 0. Are you getting my point?
Yeah, in that case.
Now the actual value is for this observation is 0 or 1.
Maybe this column name can be mentioned as probability for class 1. So it will be more clear.
Yeah, this is probability of
Class 1.
class 1. But anyway, in your sklearn package, whatever the probability that it is giving, it is actually giving for the class 1 only. Based upon that class 1 probability only, it is making its decisions also internally. Right? So if somebody simply giving the probability output of a logistic regression, you have to consider that as a probability of class 1. Now you got the point why I have written this as good.
So when we say class 1, it is always sklearn assumes that 0.5% of 1.
Yes.
Instead of 0 and 1, 1.
Yes.
Okay. Okay.
Who raised this? Someone have some kind of confusion over how I written good for 0.2.
Yeah, me sir. Yeah.
You got the point?
Yeah.
Right. So with respect to this number 0.2, we are writing with respect to class 1, but here the actual output is 0. So I need to predict something as 0, and I'm getting my class 1 probability as 0.2, which means with the 80% confidence, it is actually predicting that as class 0. So it's a good prediction. Then how can I write for 0.6? This
0.4.
observation.
1 minus
1 minus 0.6. And how can I write for the last one?
1 minus 0.01.
So if I just write this once again, like 0.9, 0.7, 0.8, 0.3, 0.4, and 0.9. Now each and every value in this equation talks about the quality of the prediction. So whenever the number is less, then it means that quality of that particular observation prediction is poor. Whenever the value is high, then the quality of that particular observation prediction is high, is good. So here I can see these two are kind of poor quality prediction. Whether it's respect to class 1 or class 0, these two predictions are actually poor quality prediction. All other predictions are kind of good quality prediction. Now if I multiply all those numbers, that is talks about the overall quality of my model prediction. If I multiply all those numbers, which actually tells about the quality of my predictive model. Suppose, for example, whenever there is actual output is 1, my probability is also exactly 1. Whenever my actual output is 0, my probability also it's actually 0. In that case, what could be the product of all those numbers?
.054.
No, you are telling with respect to this, right? 0.0544, you are telling for this. What I am asking is, say you have a table like this. Actual and probability of class 1. So 1, 1, 0, 1. The probability also exactly you are getting like this. Probability also exactly you are getting like this. Exactly the probability is 1 or 0.99999. So you can consider that as 1. Similarly, 0.000001, you can consider that as 0. So in that case, what could be your products? If you do a product like this, what could be your value?
0.
Close to 0.
No, it is 1.
How can you write this kind of expression for this?
100%, 100.11.
Into 1 minus 0 you will write, no? For 0 class.
Yeah, yes.
Then into 1. So obviously if you multiply everything, it comes as 1. Right? So the maximum value for this kind of analysis, it's equal to 1. So everyone agreeing this? For a very good prediction, a very good ideal optimal prediction, the maximum value that you are getting for this operation is 1. Is everyone agreeing that?
Yes, sir.
So now we are getting something as 0.0544. So using this only, we are actually going to compute our coefficients. Now the idea is this equation that we have written is actually known as likelihood equation. This equation is known as likelihood equation. Can you relate it? Why we are calling this as likelihood? Why we are calling this as likelihood?
Because it's a product of probability, likelihood of 1.
To get the
how likely this belongs to 0, how likely one output is belongs to 1. That is what we are modeling here, right? Yes or no? See, what is the meaning of this 0.9? What is the meaning of this 0.9?
90%.
90% of chance it is 1.
How likely it belongs to the class 1? How likely this belongs to the class 1? How likely this belongs to the class 0? How likely this belongs to class 1? How likely this belongs to class 0? How likely this belongs to class 0? That is what we are writing here, right? If it is close to 1, then it means it is actually each and every sample is actually belongs to its correct class. If the likelihood is actually anything close to 0, then each and every observation is my model is predicting correctly belongs to its corresponding class. If the likelihood value is less, then my model is predicting that particular observation with less probability. Even though that class is actually 1, actual class is 1, my model predictive probability is 0.6 or 0.4, which means there is some deviation to the actual value and the predicted probability. So likelihood is the measure through which we can understand the quality of the prediction. Say you have two models. For example, say here I am writing. This is model 1 and this is model 2. This is actual and this is probability. Again, here it is actual and here it is probability. Say the actual value is 1. Right? So here I'm just getting the probability value as yes, for that same data, I'm using one another model, model 2. Which is predicting this with this probability. So which model is the good model? M1 or M2?
M2.
So, but in sklearn, if you compute the accuracy of the model, both the model accuracy will be same. Are you agreeing that?
Yeah,
because
compared to 0.5.
But I told that sklearn will work with the threshold of 0.5. With the help of threshold of 0.5 probability, it is correctly classified. If I ask you what is the class probability, this is belongs to one class, right? This also belongs to one class. This is belongs to 0 class. This is belongs to 0 class. Because with respect to the probability of 0.5, these two probability are less than 0.5 and these two probability of greater than 0.5. So it is actually making these two observation as 0 class, these two observation as 1 class. Here also the same output. This will become 1, 1. This will become 0, 0. So in terms of predicting the output, both are actually doing in a same way, right? But if you see the quality of the prediction, the quality of the model 2 is well above the quality of the model 1. So everyone agreeing this point? If no, please ask me. Everyone got this?
Yes,
why
sir.
I'm saying that M2 quality is better than M1? So if I ask you quantitatively, tell me, you have to apply in this formula, yes or no? If you apply this numbers in this formula in this way, for which model you will get high likelihood, and for which model you will get the likelihood value with some lesser number?
M2 will get high likelihood.
Right, M2 you will get a high likelihood because the product is 0.9 into 0.8 into 0.9 into 0.8. If I compute likelihood, for 1 as it is I have to take, for 0 I have to subtract it from 1. So 0.9 into 0.8 into 0.9 into 0.2, that value is a little bit high. But here if I'm multiplying this 0.6 into 0.55 into 0.9 into only 0.555. So which is actually a kind of lesser number. So by seeing the likelihood value, we can comment about the quality of that model. So this actually is going to be used as an likelihood function or cost function to compute the model. So now the to compute the model coefficient. Now the concept is, what is the value of B0 and B1 are all the coefficients. So here in this toy case, we have considered B0 and B1. So the concept is like, what is the value for B0 and B1? We will produce the maximum likelihood value. That is what we need to find. So that is what the objective function. Are you getting my point?
Sir, one question.
Yeah.
Sir, as long as these M1 and M2 are like predicting the same values, what do you mean by like good quality, or like what's the use of likelihood then? Because
No.
both.
Yeah, I understood your question. But the thing is, say like, I'm just saying this for concept, but ultimately that model needs to compute its B0 and B1, all those coefficients, right? How you arrive with this model M1 and M2? So model will internally do some kind of computation and it need to compute this B1 and B2, right? So for that computation of B1 and B2, like in OLS or in gradient descent, we will apply different value of B1 and B2, and for which value of B1 and B2 our MSE or SSE is less, that B1, B2 will be considered as the final model coefficients, right?
Yeah.
So similarly, here in logistic regression, it
Sir, we lost you, I guess.
it will use it to find the log likelihood, and for which
Sorry to interrupt.
combination of B1 and B2.
Hello, we lost you for a minute, Sunil. Can you please repeat?
Yeah. Yes, Sudha. So in linear regression, we just randomly assume the value for B0 and B1, and we will just compute in a gradient descent way or in OLS way. We will compute for which value of B0 and B1 our MSE is less. Similarly, here in logistic regression, we will take different value of B0 and B1, that is the coefficient, and we will compute like for which value of B0 and B1 the likelihood value is high. Are you getting my point?
Yes, sir.
Right. So even though here, for example, I have told like M1 I have constructed, M2 I have constructed, this concept of likelihood we are going to use to construct this model M1 and M2.
Okay.
So this M1 and M2 is constructed with say some B0 and B1, and this M1 and M2 is constructed say some other coefficients B0 and B1. So this B0 and B1 is actually making this prediction, but in a kind of fluctuated way. Whereas this B0 and B1 is actually making this prediction very confidently, because the chance here, if you see the probability value for with respect to this B0, B1 is just above the boundary for this particular case. For the first case where the actual value is 1, my probability is only around 0.6. It's 60% probability, it is telling that it is 1, but still there is a 40% confusion over it. It's because this B0 and B1 is not tuned properly to reduce this likelihood value to the very least value. Whereas here this B0 and B1 is tuned such that it has been computed for the very least likelihood value. Sorry, very high likelihood value. Got the point?
Okay. So like if we have to say, even though both are predicting correct, it is just like how confidently it is predicting.
Yes.
Right?
Yes.
Okay, thanks.
Right. Now my question is, for your model you want whether the likelihood to be high or low?
High.
High.
Everyone agreeing that the likelihood value should be high. But here you are seeing some value, no, 0.0544. Satyanarayan printed that. So this value, are you seeing, what is your take after seeing this value? Is it a very high value or low value?
Very low.
It looks like a kind of low value, but you are, say, with respect to this table only, we have done this, right? So with respect to this table only, we have computed and the value is 0.054. Do you think that this prediction is that much poor?
No, sir.
No.
Right?
No.
So many goods, moderately good is there. Only one very bad, one kind of bad. But for that itself, we are getting the likelihood value as very low. This is because of the overflow problem. Overflow of numbers. Because probability always in terms of fraction, right? Ultimately, we are multiplying only the probability. Probability is always in terms of numbers, in terms of fractional numbers between 0 to 1. If you multiply one fraction number with another fraction number, it will become much lesser number, right? Yes or no?
Yes.
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 Even say multiplying one with one, fine. One probability is one, the another class probability is also one. Then if I'm multiplying it, then it is one, good likelihood. But even if I multiply 0.9 with 0.9, 0.9 is a good probability range. But still, if I multiply with 0.9 and 0.9, my likelihood will become 0.81. It's actually reducing below that. So that is the problem. So if we multiply so many fractional numbers, then obviously the overflow will happen. It will move towards the zero. It will move towards the zero. So that is the reason why people will compute likelihood in terms of log. In terms of log, people will tell this a log likelihood rather than just defining this as likelihood. We have to define this as log likelihood, because by taking the log, we can handle this overflow problem. Are you getting my point? Why we need to take the log for likelihood?
Why not average?
Average.
Not average.
Just adding all those things and taking the division by total count.
Yes.
But it is, what is the it is not a kind of balanced representation. It is like, say, error. How will we computed the error? For each and every observation, what is the deviation? That only we modeled, no? There it is not a scaled one. Here it is always a scaled one, right? It is actually always between 0 to 1. Whatever the individual likelihood number that we are going to get, it is only between 0 to 1. So there is no meaning in taking the average and bringing this into a kind of mid-level, right? So we are just multiplying it, and if that multiplication, that is why I have even shown this example. Say here, everything is here in this example. If everything is actually same, that is that probability value and actual value is ditto same, then definitely we will get the likelihood value as 1. The more the deviation, the likelihood value will reduce. More the deviation, the likelihood value will reduce. So it is already scaled with respect to 1. So we no need to take that average to bring that mid effect, something like that. For the good fit, for a very perfect fit itself, that maximum likelihood is going to be only 1. So with respect to that, if there is a deviation, how much reduction will happen? That we are actually modeling. Maheshwari, can we always likely high considered here? Always. Yeah, of course, always the high value of likelihood that we want. Whether in terms of log or whether in terms of ordinary number, we want the likelihood value as high. But of course, I'm going to tell one another concept. Just hold on. As of now, you just understood like why we are taking log. Any doubt in this? Why we are taking log? Can I move to the next one?
Sir, I have a doubt. So
Yeah.
log of this value is negative. What does that mean?
Yeah.
Log of 0.05.
Yes. So for this, you will get the negative value, right? So you just apply it. You just apply it for some other bad prediction. So in negative value, it will increase. The negative value, it will increase, right? For the other bad prediction, in terms of negative value, it is increased for further bad. For the further good prediction, in terms of negative value, it will reduce. So you don't need to much worry about that negativeness of the log. Just you can consider only the polarity. Just you can consider only the polarity. That is sorry, not polarity. Just you can consider only the magnitude, right? Taking the log, you just consider the magnitude, whether the magnitude is high or low. That actually talks about the quality of your likelihood, right? Because always it is negative only. If you take log, do you think that the value will become positive for likelihood? For the likelihood, do you think that log will become log will give you the positive?
No.
Right? Why?
Log 1 is 0.
Log 1 is 0. The maximum likelihood that we can get is actually 1. So that is the reason. That is the reason. If you see in literature, whenever people mentioning the log likelihood, they have mentioned as negative log likelihood. They have mentioned negative likelihood. So what they will do after taking the log of the likelihood, they deliberately take the negative of it. So only magnitude they will keep, no?
Yes.
So because there is no way that likelihood, log likelihood by default comes in positive, because the maximum likelihood that we will get is 1. If you take that log of it, definitely we will get it to 0. But if you multiply any probability, definitely we will get the overall likelihood in terms of fraction. For the fraction number, if you take the log, definitely we will get the negative. That is the reason people just discard that negative, or people will call that as a negative log likelihood ratio, so that they will consider only the magnitude of part of it.
Okay, got it.
Right? Fine. So just a couple of minutes before we take a break. I just formulate this expression. Whatever that we have written, can I write like this? Yi What is the meaning of this?
It's log loss.
No. Can you relate the previous workout that we did with this equation? See, for example, I have actual output y and it is probability. Say if it is 1.9, if it is 0.2, if it is 1, say 0.7, if it is 0, say 0.4. Now, if you substitute this in this equation, what happened? With respect to the first observation, what is yi? 1. So 1 into
log of 0.9.
Log of 0.9 minus 1 minus 1 into log of 1 minus 0.9. So for this expression, this is the equation, right? Yes or no?
Yes, sir.
Yes, sir.
So this part will become 0, right?
Yeah.
Which means we have left it with 1 into log of 0.9. So that is nothing but only log of 0.9. So if I ask you to find what is the likelihood of this one particular observation, you will tell 0.9, right? Likelihood of this one particular observation is 0.9, right? Yes or no?
Yes, yes.
So now the same thing only here we are getting after applying in this equation. Then for the second observation, what will happen? For the second observation, if you apply in the same thing, what will happen?
0.8.
So if I apply the second observation also here, because here summation term, so I have to put plus. For the second observation, what happened? That yi is 0, right? Yes or no?
Yes.
Yes.
For the second observation, yi is 0. So here it is log of pi. Pi is say 0.2. Then minus 1 minus 0 into log of 1 minus 0.2. If you solve this, this part will become 0 and this part only will have the value. What is that value? Log of 0.8. Log of 0.8. Yes or no?
Minus log
Yeah, minus log of 0.8. But anyway, if it is a negative log likelihood, negative log likelihood, if I model this as negative log likelihood, this formula itself in front it's having one minus, right? So in that case, that minus and minus will become plus. So which means basically if I compute the likelihood, it will become like 0.9 without this log concept. If I find the likelihood for this example, 0.9 into 0.8 into 0.7 into
0.6.
Right. If I use this equation, what it will happen? I can write this as log of 0.9 plus log of 0.8 plus log of 0.7 plus log of 0.6. Are you agreeing this?
Yes.
I'm just simply taking the log of all those products. So once we take the log, the product will become sum. So log of 0.6 plus log of 0.8 plus log of 0.7 plus log of 0.6. If it is negative log likelihood, then for this whole thing I have to put minus in front. Minus in front.
It's near to 0.
Sorry?
It's near to 0, the value of whole equation.
Yeah. So but anyway, now has been modeled like this. Model like this. So if you applied each and every observation in this equation, you will end up with this equation. You will end up with this equation. Simply taking the likelihood and taking the log of it and put minus sign in front will become negative log likelihood. So this is the equation for negative log likelihood, and this negative log likelihood is nothing but the cost function of your logistic regression. Loss function or cost function of your logistic regression is actually known as negative log likelihood function. It is also, people sometimes will also call it as entropy loss function. But anyway, this equation properly we are going to call as negative log likelihood function, which is going to be which is going to be used as an cost function or loss function to optimize the parameters or optimize the coefficients. Understood?
Sir, one doubt here. In this
Yes.
log, we have to multiply, right? Why are we adding it? A log of 0.9 plus 0.8?
The thing is, say in base math, say log of a into b, you can written as log of a plus b, no? Log of a plus log of b, no?
Okay, sir. Yeah.
Right. So that is the reason. So that say because of that only that the overflowing problem is overcome here. Say if you simply multiply all the fractions, the resultant value will become close to 0. But as we are adding that log value, it will actually increase. No, it won't actually running into 0.
Right. I got it, sir.
Yeah. That is one reason why we are taking log. Any doubt? So I think we can release the poll now.
Yes, Sendil. And are we giving a break now?
Yes, they can take a poll and they can move for break, no?
Yes, sir.
Yeah.
Yes, I'm launching it. Students, please look at the poll and give your answers. Students, are you all able to see the poll?
Yeah.
Yeah.
Okay. Okay. Going forward, all the observations also will be recorded. Okay. So please actively participate so that we'll come to know you whether you understood or not. And we'll
I
also,
will not hit the submit button.
you're not getting submit button?
Oh, okay, okay. There are three. Okay, sorry.
There are 3 questions.
Okay.
We'll also come to know who's active and who's not. Okay. So please go through the questions and answer.
So can't I see the response?
I don't think so, Sindhu.
Okay.
Ma'am is submitted after that.
You can take a break now.
15 minutes, right?
10 minutes. Take 10 minutes break.
Okay.
Students, complete after completing the poll, you can take a break, and then after coming back, we will discuss this. I see only 15 students have voted. Students, still 17 students have to respond. Please respond soon. Are you all active?
Ma'am, we will not be able to see.
Yes, ma'am. Submitted.
Okay, okay. Those are submitted can leave for a break. Only 60% have voted. Please submit. Guys, I'm going to close it in a minute. Please respond soon.
Ma'am, last one, which formula it was where we have to
Just
calculate
now, sir, discussed,
without log?
Guys, I'm going to end the poll. I don't see 10 people have not responded yet. So from next class, you will be marked absent if you are not responding to the poll questions.
Where to get the results?
I will share. I will immediately, you can see. Okay. Once I end the poll, I will share the results.
So red one is the correct poll. I mean, where maximum people voted.
I think you can see the majority opinion only. Sudha, is it like that only? No. For which option many people choose that?
I will send a screenshot, Sindel, to your WhatsApp number.
Sure.
Ma'am, we'll assume the majority as answers, right? For this.
Yeah, let me see that majority answer and.
Yeah, we will discuss. Please wait.
Hope that will be a correct answer too.
Senthil, were you able to see the results, poll results?
Yes, yes, Sudha.
Yeah, okay. I think we can discuss that and start.
So I can see 70% of people given the correct answer for the first question, and but I'm wondering 30% of people still went for other options. So the question is very simple. Compute the R. So just now we have discussed, what is the equation for R ratio? P divided by 1 minus P. So the probability of diagnosing a person with cancer is 0.3. I have given, which is nothing but P value. So P divided by 1 minus P. So it is like a 0.3 divided by 1 minus 0.3. So 0.3 divided by 1 minus 0.3, 0.3 divided by 0.7. I think the answer is 0.4285, right?
Yes.
Right. So which is just you have to apply what is you need to know what is the odd formula, and you have to substitute P value in place of it so that you will get the answer. The second one is simple, straightforward. Logistic regression output follows which one of the following function? So I told categorically right that function is e to the power of z divided by 1 plus e to the power of z. We have discussed why that equation, and also we just reframed that equation as 1 divided by 1 plus e to the power of minus z, and we have executed that equation. After doing all those things, I have even taken you to the board again, and I have plotted it. If you plotted that particular equation for different value of z, obviously you will get a kind of curve. That curve I have named as what?
S curve.
S curve, sigmoidal curve. S curve or sigmoidal curve. But some of you actually given the value as log. So we have not actually called that as a log curve. It is actually a sigmoidal curve. Of course, logarithmic part obviously will be there in it, but for that we can't call that as a log curve. That is actually a sigmoidal curve with two kind of tiles on both sides. And for the third question, the actual output of two observation is 1 and 0. And my model is predicted the output in terms of probability as 0.7 and 0.2, which means for the class 1, it is producing the probability of 0.7. For the class 0, it is actually predicting that with a probability of 0.2. So I told that the probability value is with respect to class 1. So in order to find the likelihood, we have to keep the probability of class 1 as it is, and we have to subtract the probability of class 0 from 1. So 0.7 into 1 minus 0.2. That is the answer, right?
Yeah.
So 0.7 into 1 minus 0.2, which is nothing but 0.7 into 0.8. So the answer is 0.56.
Senthil, are you sharing your screen?
No, Sudha.
Okay. Yeah, okay, fine.
Just now I have shared. So still anyone have any doubt with respect to these three questions, especially the ones who gave the wrong answer? If you have any doubt, please ask me.
Sorry, I missed the third answer. I was having a network issue. What was the last answer alone?
Answer is 0.56. Why we have got that answer is
0.7 minus into 1 minus 0.2.
Yes, 0.7 into 1 minus 0.8. So as the probability value always indicates the class 1 probability, in order to find the likelihood, we have to keep the one probability as it is. For the 0 class, whatever the probability which is model is throwing to us, we have to subtract that from 1, and then we have to multiply. So here for this case, 0.7 into 1 minus 0.2, which means 0.7 into 0.8. So the answer is 0.56. Okay, so with this, you can go to the Jupyter notebook, and we will take one real data set, and we will apply this logistic regression model that we have discussed on that data set, and we will evaluate its performance measure and all those things. So everyone have one admission predict data set with you, right? Is everyone having that data set?
Yes, sir, we have.
Let me bring the chat window. This one is fine. Just load the data. So before I'm taking you into this study, let me just brief you about one point. So we understood that the log likelihood equation is this one. Once again, I'm just writing it. That the negative log likelihood, NLL. Negative log likelihood equation is summation over I. In front, I can put on minus sign, or this minus sign I can internally even put for each and every term. Yi into log of Pi minus one minus Yi into log of 1 minus Pi. So this is the expression that we have proven how this equation has been modeled and all those things. Now my question is, if you plot this, what is the kind of response that you will get? I told that this is the loss function or cost function. This is the loss function or cost function for logistic regression. Similarly, we know what is the loss function or cost function for linear regression. That is summation of yi minus b1 x1 minus b0 the whole square. Right? So this is the cost function of our linear regression. If we plot this cost function of linear regression, what kind of curve we will get?
So why there is no limit in I, summation of I and the range for I?
Yeah, that has understood. No, so that is the reason I have not written. That is I equal to 0 to n minus 1 for each and every sample.
Okay. Yeah.
Right. So here the summation of yi minus b1 x1 or xi minus b0 the whole square. If you plot it, what kind of curve you will get?
Parabola.
Parabolic, right?
Convex, yeah.
With respect to this only, we have discussed gradient descent and all those things, right? So similarly, if you plot this, what kind of curve you will get? It is difficult to just say by seeing this equation, but there are some proof in some standard mathematical literature, you can go through it. It has been proven that for this equation also the curve is a kind of parabolic only, right? Because if you see log, and here it is, the expression is here like it is log of function, here it is log of 1 minus something. So it is like 1 log will give you something like this. The another part of this log equation, it's going to be something like this, so that the resultant graph size or resultant graph shape of this equation is once again a kind of parabolic curve. Once again a kind of parabolic curve, right? So there is a mathematical proof for this, but anyway, just keep that in your mind. Like, even though this equation is having the log part with the pi and log part with 1 minus pi, if you decode it and if you plot it, this also can be drawn as a kind of parabolic curve, as we used to draw this. This is straightforward, it's a square function. So any square function, we know that it's a parabolic curve, but here it's a log function. But if you see log or exponential, if you plot it, you will get a curve like this. If I e to the power of at, if I plot for different value of t, definitely I will get a exponentially increasing curve. Similarly, e to the power of minus at, if I plot it, I will get a kind of decaying curve. If I'm joining, if I have both e to the power of at and e to the power of minus at in my graph or in my equation, then here something exponentially increasing, here it is exponentially decreasing. So I am just getting a kind of parabolic curve. So here exponential can be related with the log also, right? So the same effect here also we are getting. So it has been proven that this cost function or the loss function of logistic regression will also give you the parabolic curve. Once we have a parabolic curve, obviously this is log likelihood, and this is your estimator b0, b1, b2, so on. So we are going to find something like for which value of b0, b1, b2 the loss function is minimum. The loss function is minimum. So gradient descent algorithm itself can be used here, as this is a negative log likelihood function. It is coming as a descent curve. Say if you are not putting this minus, if you are just keeping this as plus and this also plus, then the curve that we are getting is like this. This is for log likelihood and this is for negative log likelihood, right? But anyway, here that optimization objective is like for which point, for which value of b0, b1, b2 my log likelihood is maximum, that I need to compute. Here if you consider negative log likelihood, then for which value of b0, b1, b2 the negative log likelihood is minimum, that I have to compute. So both are actually a kind of same only. But only thing that you need to remember is, or keep in your mind is, even though this optimization, even though this loss function, it looks like a kind of log equation, this log equation also, if you plot it, you will get an parabolic curve only. You will get an gradient descent curve or ascent curve. In case of positive log likelihood, you will get an ascent curve. In case of negative log likelihood, you will get a descent curve. So the optimization objective here is, what is the value of b0, b1, b2, so on, which will give me the less negative log likelihood. In case of log likelihood, what is the value of b0, b1, b2, which will give me the maximum log likelihood. So that we are going to find out. Of course, that math internally will happen with respect to this sklearn package. There are so many ways. Say a few algorithms let me list out. If you are interested, you just go through the math part, but that is not the objective of our session. So one famous algorithm is Newton CG. It's like Newton Raphson, right? Then another one is there is one function called liblinear. So which is having the it's a library of linear functions, something like that. Library for large linear class, something like that. So this is one library in which there are so many solvers are there. So your logistic function use that library and to solve this b0, b1, b2 values. And also there is one another algorithm like SAG. This is actually stochastic gradient descent. And also there is one another algorithm as Saga. Again, this is stochastic gradient descent modified version to handle large data set. Right? So these two functions actually are these three algorithms. These not three. Of course, this is not one single algorithm. It's a kind of library. I can't call this as an algorithm, but anyway, these four methods are available in your sklearn package to compute the coefficients with an objective of minimizing the log likelihood value. With an objective of minimizing the negative log likelihood value. Right? So
Sir, one question here. So what is the best use of this, all the algorithm? Which conditions should we use, and what is the best performance and
there is some kind of literature is there. I will share. But here, if you see, this Newton-Raphson method will use something called Bayesian matrix. This Bayesian matrix is actually the second derivative. We used to take the derivative, no? So we will be say if you want to find this minimum
I
point.
think this method we are using XGBoost.
Yeah, so say if you want to find this minimum point, for this minimum point you have to take the derivation of this equation, and you have to equate to 0. So this Newton method is actually doing the second order derivative. So second order derivative and equating the 0 and formation of this Bayesian matrix. There are so much of mathematics, so which actually proven that it takes a lot of time. The complexity is more. The complexity is more with respect to the Newton CG. So obviously for the lesser data, it will work. For the big data, for a complex data, it takes a lot of time, and also sometimes it won't converge with respect to lesser iteration. We have to pass more iteration. While we doing this work also, sometimes we will getting the warning like, by default, the number of iteration is say 500. Within 500 iteration, this algorithm may not compute the optimal value of B0 and B1. So that time it will give you the warning. So what we need to do, we have to increase the iteration size. So like that, in terms of complexity, this Newton CG method you can apply for some small data. Generally, this SAG and SAGA is for big data. So if the data size is big, because it is working in a stochastic approach, we know, right? It will divide your data into different blocks. For each and every block, it used to compute, or it used to tune those coefficient value. So quickly you can come up or arrive with the correct numbers. And also SAG will handle this problem of local minima. So in this sense, SAG is a little bit good, especially while handling the large data set. And this liblinear, as I told, there is no one way liblinear. So this is actually one function, one library. So there is one conference a few years back. There is one conference happened. So whatever that conference happened with respect to this linear equation solutions. So whenever somebody want to find the solution for different equation, to find the global minima, local minima, and all those things, they have presented the different approaches in their conferences. So the selected approaches which has been presented and accepted in that conference has been generated or has been framed as one library. So it is like a kind of research. So many people come up with their own approaches to solve the equations, to find the global minimum, global maximum, and also so many other mathematical tasks for which they have provided the solution. All those solutions has been combined, and with respect to the conference, whatever the things which has been presented, which has been combined, for which people developed the programming logic also. All those programming logics are available under this package, liblinear. So that is what the idea. We can't actually really go deep into how each and every math part of that works. But basically, it's a gradient descent. The differentiation and taking that differentiation and equating to 0. In that way, only all those algorithms fundamentally works. But of course, with respect to the optimization purpose, they have done a lot of modification in it. If you're really interested, you can go through the research papers are available for each and every algorithms we can go through in order to understand that in a deep way, but that is pure math, right? It doesn't, it has nothing to do with data science purpose. For us, we need to know the value for those coefficients, so that with that we will compute or with that we will infer so many things with respect to the business perspective.
Okay.
Got this point?
Yes, sir. Yeah, thank you.
Others? Because I have told the loss function, but how that loss function has been used to compute those coefficients, that idea you should have. Any doubt? I think someone started to ask something.
Sir, one basic question. Just in the above, this values, the sigma value is to calculate the overall probability, right? So actually, the value should be high, is what I have taken. I mean, I have noted down. But why are we taken the lowest point again?
No, that high in terms of log likelihood, that value must be high. But if you are taking the negative of it, then we have to do analysis like that, for which combination of B0, B1, B2, the negative log likelihood is minimum. In terms of log likelihood, if you see the value we want to be maximum. If you see in terms of negative log likelihood, if you keep that negative symbol also in your expression, then we have to look for what is the kind of combination of coefficient which give me the least value for negative log likelihood.
Okay, sir. Okay, got it. Yeah.
Right, because many of the defined algorithms are gradient descent algorithms. But here, basically, if you see log likelihood, then we have to apply gradient ascent algorithm. So in many packages, we have only gradient descent algorithm. So in that sense, it is also good to represent this into a negative log likelihood. So we can simply apply our traditional gradient descent algorithm to find those coefficients. That is what the idea behind it.
Okay, sir. Yeah, got it.
Right. So now let me take to the Jupyter Notebook. I hope every one of you loaded this data. So I'm not going deep into that EDA part of understanding this data. I just let that part to you people. Only the required EDA with respect to the model building quickly we will do. Just before doing anything, so what is the output column in this data set? What we actually want to predict from this? What is the target column in this data?
Getting admission.
Getting the admission, right? So it's a university is running one machine learning model in their campus. So once they receive the application from different people, they are actually running it in their algorithm, and they are actually shortlisting the students and with respect to their model itself. So who can be called for an interview, because calling somebody needlessly for an interview is a waste of time, right? So it's a kind of algorithm through which we can understand, or if you build this model and if you put this under one server, and any student can come and enter their information in their college portal, and they come to know whether they have the chance to step into that college or not. So they won't even spend for buying their application, right? So it's just a kind of a model to just predict the chance of getting admission in that particular institution. So we are making that decision with respect to the different input columns like GRE score, TOEFL score, university ranking, and SOP, LOR. So these are some kind of measures with respect to academics. Of course, CGPA, whether they have research experience or not, right? So let me, by seeing this data directly, can you tell, is there any data which is not at all important?
Serial number?
Serial number. So serial number we don't really need. So I'm just dropping it. Data equal to data dot drop off serial number 1. Then quickly check the missing values for the remaining data. So there is no missing value. So we no need to actually perform any kind of missing value treatment. So prior to build the model, and also I can't see any categorical variable. Of course, there is one categorical variable which is nothing but research. So, but research is having 1 and 0. But anyway, it has been already encoded as 1 and 0. It is not having string as yes or no. If it is, then I have to convert that yes into 1 and no into 0. That kind of task is also not really exist in this data set. So I'm just taking my output variable separately. Out equal to data of chance of admit, and my input is equal to data dot drop of chance of admit, comma 1. So I have taken my input and output separately. So of course I no need to do the encoding, but whether I need to do scaling, whether logistic regression, you feel whether it is sensitive to scaling?
Not necessary.
Not necessary really, but in terms of say in linear regression, what is your take on scaling? In which scenario in linear regression we will do scaling?
Regularization.
Okay, that is one part, regularization. The other
PCA,
thing,
if I'm using PCA kind of.
okay, PCA. The other thing,
after removing outliers to build the model,
the gradient descent. So whenever you are applying some kind of that gradient descent approach to find those coefficients, gradient descent convergence will happen quickly if you have a scaled data. This point we have discussed, no? Yes or no? No one remember that point?
Yeah, yes, sir.
Right. So because in gradient descent, something need to be, some high error need to be bring down to some kind of low value. So obviously, if we have a scaled version of data, then obviously that will actually bring down our error from some high value to low value quickly. So here also, I have listed some of the algorithm which has been used by your sklearn package to actually reduce this, to actually find those coefficients. So in that context, it is healthy to scale your data. It is healthy to scale your data. Of course, in terms of performance, it won't affect. That is in terms of accuracy score or some measures like precision recall. All those things we are going to discuss now. But in terms of calculating those coefficients very effectively and quickly, so scaling may help. So in that sense, quickly I'm just doing the scaling from sklearn dot preprocessing import standard scaler. So sc.fit transform of. So do I need to do scaling for all the columns in my data? Input data?
numerators.
Huh?
Only numerators.
Yeah, of course, but you can see all looks like numbers. But anyway, do I need to scale for apply scaling for all the columns? Yeah, binomial
research.
Research for binomial column, we no need to actually really apply scaling. So what I'm doing here is input dot iloc of colon comma up to -1. That -1 is exclusive. So which means for the last column it won't do scaling. For all other columns, just do scaling. But we know that after doing scaling, we will be losing out that column information and other things because it's converting our data into what? NumPy array. So I'm just bringing back once again to data frame. So input sc comma columns, which is equal to inp dot columns of So I'm just reassigning the column name once again from my previous data frame input. That input research column also is there, but I have not used that research column here for scaling. So I'm just passing all other column titles to this scaled data by excluding that research column alone. Right. So I'm just copy paste this in your chat window. So now we have INP SC dot head of 2. Fine. So, but I don't have research in it. I have to bring back research. So what I can do, input underscore SC of research, which is equal to input of research. So if I see this, so obviously I have now research also in my data frame. So all other values are scaled value. Research is there as it is. So everybody treated your data up to this?
Yes, sir.
Right? Fine. So let me discuss one more thing before going into the implementation of this. So while we discussed linear regression, we have discussed a lot of assumptions. Before building the model, we make sure that all those assumptions, or before finalizing our model, we have checked all those assumptions. Do you think that all those assumptions are really necessary here also?
No, sir.
Say normality assumption. Whether is it any logic in applying the normality assumption here for logistic regression? Yes or no? If yes, why? If no, why?
No.
No, because
The
we
score
are
is independent. So
No, we don't require actually.
we don't
Because the
have.
target is
Yeah.
complete.
Exactly that point. So the normality assumption in linear regression, we have checked for what parameter or what entity?
Errors.
Residuals.
Residual. Right. That residual, that error, which is continuous in nature. Here, that output column is actually only having two levels, 0 or 1. There is no point in doing or checking the normality with respect to that output column, right? Yes or no? Is everyone getting this point?
Yes, sir.
Yeah. So there is no point in actually applying the normality or checking the normality condition that we generally usually do for linear regression, because that output need to be normally distributed so that the error also normally distributed. Here there is no way that we can calculate something called a continuous error, and also our output column is not continuous, so we no need to worry about the normality assumptions. Then what about the other assumption, linearity? Again, that linearity assumption, or really if there is any kind of linear trend, then obviously my model will learn effectively and it will give you the very correct output. But it is not like if we can check the linearity, because once again that linearity, if we want to check, the output column should be continuous. Here again that output column is not continuous, so obviously we can't really check whether our data model or data is linear or not. But the thing is, if there is a kind of linear relationship exists, your model will produce the better result. So if more non-linearity exists in your data, then obviously logistic regression will produce less result. So by seeing that result in terms of accuracy, in terms of any other measure, we can understand that really we no need to actually check prior to build the model. Then homoscedasticity and other things, again all those assumptions are actually with respect to the output column or with respect to the residue. Here there is no concept of residue, here there is no continuous output column, so there is no point in applying all those assumptions, autocorrelation, homoscedasticity, linearity and normality. Then what is the one assumption still I have not explained?
multicollinearity.
multicollinearity. So what your take on it?
We need to have little multicollinearity.
Yeah, we should check multicollinearity. Yes.
Yes, we should check multicollinearity. Why?
Because again, it can bias our model. That is because two features will keep same information. So
duplicate data.
Yeah.
So again, morning itself we have discussed on the line of how to make our model more explainable, right? So that is the reason why we have from P we have computed order ratio P divided by 1 minus P, and from that we have computed the logit of P divided by 1 minus P and all those things. Why we done that part?
We calculate the coefficient, and multicollinearity can impact the coefficient also. So.
Exactly. So we that interpretation part will be affected by the multicollinearity. So while we are explaining any one variable with respect to the target, the assumption is we are keeping all other inputs as constant, right? What is the 1 unit increase in x1 which will affect my odd of getting cancer? By keeping all other input are constant. That is the idea. So that concept itself here will be that explanation we can't do properly if we have multicollinearity in our data. So we have to check only one assumption really with respect to the logistic regression, but people will tell some other assumptions like the output must be categorical, and also you should have only 2 level. That and all kind of must think, right? We can't apply logistic regression when our output is continuous in nature. So that we don't need to really consider as an assumption. The main assumption that we need to check is multicollinearity, because if multicollinearity exists in our data, that explainability about our model is not trustable. So in that sense, we have to check the multicollinearity. So quickly, I want to check the multicollinearity for this data. But anyway, what I do is, as we already have this code, we already done this part, right? So once again, no need to waste time by typing this, because for so many times again and again we have done this during our previous residency. So I'm just copy pasting it, and also I copy pasted for you people in chat window. If you have your previous script, you can use from that also. So here you just change that variable name. Here we have as input underscore sc. Do you think that really this data is suffered with multicollinearity? After seeing this number?
Acceptable.
It's acceptable, right? So slightly one number, it's more than 5.2, but it's well and good. Anything less than 5 is really good, but 5.2 is not that much dangerous. So I'm just keeping all those variable. I'm not going to drop any variable saying that it is having the high multicollinearity. So, but anyway, this is this you have to check prior to build the model. This is the only assumptions you need to check. So if you feel like some column is having high collinearity, you can drop it, and you build your model with respect to the other features. Then only the kind of explanation that you are talking about with respect to the coefficient can be true. So once I did this, I'm going to build a model. So always we are going to build the model only for the training, and we use some section of the data for testing, right? So during our initial linear regression session, we have not really concentrated that part. But anyway, at the end of our linear regression session, we used to do that strategy a lot, right? Because any time in machine learning model, we have to make sure my model is not overfitting. One easy way to understand the overfitting nature of the model is, don't use all the data for model training. Only use 70% of data, 80% of data for your training, and test your model with the remaining 20% of data. And that will give the kind of clear understanding whether your model is learned properly or not. So in that context, I will be splitting my data into train and test. So from sklearn dot model selection, import train test split, and of course xtrain, xtest, ytrain, y test. Be careful while giving this order. Sometime I used to see people will give x train, y train, x test, y test. That is wrong. So first split must be on input, then on the output. So x train, x test, y train, y test. Train test split of my input SC, comma my out, comma say test size. I'm just giving 0.2, 20% of data, and that I'm using for testing. Say random state. Say here I'm just using 10, right? So I have used the random state 10. Also, I encourage you people to use the same so that we can cross check our results. So I have split my data into training and testing, 80% for training and 20% for testing. So now I'm just building my model. So
Sir, for random state, what value we have given?
I have just given 10. So it is not like any number you can give, but if you and me given the same number, then my result and your result can be comparable.
Okay.
Because say randomly it will just take 80% of data to train and 20% of data to test. So in your system, it may randomly pick in its own way. In my system, randomly it picks in own way. So in order to freeze that in your system and in my system also, if it need to pick in the same way, provided that all our system specifications are same, if both of us give the same random state, so the way that it is splitting the data will be the same. So that is the reason why I ask you people also to give the random state equal to 10. Fine. So once I done this, I'm just going to implement this model first using the OLS package, and then we will be implementing this using the sklearn package. So the function import stats model as SM. So from this, I have function called logit. Previously, we have used the function like OLS, which is for linear regression. For logistic regression, we have function called logit with capital L. I'm just using this logit, and for that, I have to passing my train portion of the data, y train and x train. Of course, this logit function, as in OLS, it used to find only coefficients. It won't use to find the intercept, right? So if we want that intercept also, then we have to add one constant column in our data. So x train c, which is equal to sm dot add of or add constant of x train. So I'm just fitting this into a logit. Just make a name, mod stat, something like that, statistical model. And in the next line, I have to fit that. So say the result model or yes, or log model or logic model, whatever. Logic mod, which is equal to stat dot fit. So the syntax is same. So I just copy paste this. Your chat window. Only thing is, in case of OLS, we have used logit.
So that should be mod star underscore.
Yeah, I don't see.
What is stat?
It should be mod underscore.
No.
That is stats, right?
No, logit and
That model start API actually.
Yeah, that is dot API SSM. Stat is not defined. What is stat? Oh, sorry, here mod stat. So is everyone getting this? Yeah, I have pasted that code with some mistake. So I am just pasting this one now.
With extend C.
Sorry. Everyone got this summary?
Yes, sir.
Yes.
Right. So here only 320 observations are there in our data and 6 columns. So with that, it is actually printing all those information. Here we are seeing something as pseudo R square, right? So what is this pseudo R square? Actually, there are so many ways that people can define the pseudo R square. There are different formula. As skewness, there are so many formulas, right? Like Bowley formula, Fisher formula, Pearson formula, like that. Here also for pseudo R square, there is different formulas because it's kind of statistical measure. People will come up with some statistical adjustment and they claim that their formula is better than others. Anyway, this logic function from OLS is actually using McFadden pseudo R square, right? So this is McFadden pseudo R square formula. Apart from that, we have formula like we have expression for the pseudo R square developed by Coxnell. There is one other scientist also, Engel, right? So, but anyway, what is pseudo R square? That is important rather than seeing how many formulas are there for it. And here in OLS package, this pseudo R square given by the formula, let me write that. McFadden R square formula is given by 1 minus, actually this is negative likelihood, negative log likelihood of your model, the whole divided by negative log likelihood of null. In other words, I can also written as NLL null minus NLL mod, the whole divided by NLL null. Oh, sorry, I have paused extend. Matthew is telling, yeah, of course, I have typed this and after I have inserted that line. So change it. Here we have to pass extend C, right? So only if we pass extend C, if you see previously without extend C, I have just passed the extend. We are not getting that constant. We are not getting that constant. So for that, that is the exact reason why we have computed something called extend C. We have to run that with extend C. So with the extend C, that is with constant, we are getting one constant also, which is an intercept of our model. Now come back to this equation. I have something called negative log likelihood of the model and negative log likelihood of the null. Any idea what could be negative log likelihood of null?
The only one model based on the intercept. So
exactly. Null model is the one which actually doing its prediction with respect to only the intercept. If you remember, even while we discussed the R square for linear regression, it's an explained variance. We have discussed or we have computed like what is the total variance. The total variance of the model we have expressed in terms of the mean model. We used to compute something as mean model by taking the average value of the output. So that is actually your intercept value. With respect to that, what is the variance? Out of that total variance, how much variance has been explained by my model? That is actually R square. Similarly, here the same concept. The only the thing is without rather than expressing that in terms of error, here we are expressing in terms of the negative log likelihood. So this is the total negative log likelihood. Say, and in the numerator, it is actually my model log likelihood. So if your negative log likelihood and model log likelihood are actually same, what happened? What is the nature? If this numerator and denominator are same, what is the meaning of that?
Zero. R square is zero.
Model
Your model is not actually doing anything extra compared to your null model, right? Yes or no?
Yes, sir.
If this denominator and numerator is same, then what it means?
Both are null model.
Both, whatever that negative likelihood value that I'm getting for a null model, the same value only I'm getting for the for my whole model also, means my whole model is not at all different from my null model. In that case, this whole part will become 1. So 1 minus 1 will become 0. 1 minus 1 will become 0. That is the worst model. That is the worst model. If R square equal to that McFadden R square is anything equal to 0, then that is a kind of worst model, which means your model is not explaining anything extra that has been already explained by your null model, right? So your whole model is behaving like a null model. And in which scenario that R square value will take the 1 here? In which scenario this McFadden R square value will take 1 here with respect to this equation?
-2.
If ratio is 0.
-2.
This ratio must become 0, right?
Yes
or no?
There one more choice also.
What is one more chance?
If you take that value as -2 +2 or -2, yeah, not.
-2 minus 2 become, right?
Yeah, plus, yeah.
It will come. So if this ratio, as this is a ratio, definitely this value only in terms of fraction. The maximum value can be only 1. So more than 1 you can't assume for this, right? Because it's a ratio. So now, so if it is 0, can you tell at which situation this ratio can be 0?
Your null NL this
infinite.
It will be 0 then. In upper part.
Negative log likelihood is 0. So if you remember, when I'm talking about gradient descent and gradient ascent, if negative log with respect to the log likelihood, the value should be maximum. With respect to the negative log likelihood, the value should be minimum. Yes or no? Yes or no? If you are measuring in terms of log just likelihood, then the log likelihood, then you want that log likelihood value to be high. If you are measuring in terms of negative log likelihood, then the value you want to be very low, right? Everyone getting the point?
Yes, sir. Yes, sir. NNL mod should be much lesser than NNL null.
Yes. So if this value is much less than this null model, the numerator is very less compared to your null model, then obviously this whole ratio will become kind of 0. So in that scenario, your R square will be 1. So that is a good indicator of your model.
So null model can have 0.
Null model, if it is having 0, then it is a kind of very simple data. Right, so say it is like whoever scoring, say you are predicting who is this good student, and whenever that average score, whenever that student score is more than 50, that is say the student average, the marks of the average mark of all the students is 50, and the trend is like that. You are labeled like that. If students than 50, they are good students. If they are less than 50, then they are bad students. If that is the only criteria on which you are making this classification, then the null model value can be 0.
Then this will go to infinite, right?
Yeah, of course. So if that is, we can't tell that it's an infinite. That we can't compute. 0 divided by 0. It is we can't call that as an infinite. 0 divided by 0. We have to consider that it can't be computed.
Sir, we can think as a loss also. NL null model, like we will get more loss compared to our model. All the all features.
That is the worst case. Like we will see R square sometime will come in negative. My model is behaving poor than the null model. That kind of scenario here in classification task, it won't happen, right? So here, even if it is a worst prediction, something like that, R-square won't become a kind of negative as we used to discuss in our linear regression. Because here it's going to be only 2 levels, right? This or that. Right? So basically what you need to understand is, if your model is doing better than your null model, then your R-square value on the higher side. If your model is actually doing same as your null model, then your R-square value will be on the 0 side. Got the point, everyone? Any doubt?
That means null model value is greater than our model, right? Always.
See,
NL of null is greater than
greater
NL
or
of null.
lesser, don't confuse. Because with respect to the negative likelihood, for a good model, I want this negative likelihood as a less value, right? So this expression, it's actually for negative likelihood. Just keep it in your mind like this. If your null model, if your whole model is behaving better than your null model, then your R-square value towards 1 your R-square value will be on the higher side. Whereas your whole model is behaving same as your null model, then your R-square value will be towards 0. Got the point? Still any confusion? Yes or no?
So that means the null model is always greater than our model.
What greater than? In terms
The
of
NL
you are asking, in terms of log likelihood you are asking. Say if in terms of log likelihood, always our null model log likelihood is more than our perfect model likelihood. Because for a good model, I want the log likelihood value to be less.
Yes.
Got the point?
For null model, it is more actually.
For null model, if you consider negative log likelihood, that value
more.
will be high.
Yeah. Got it.
Right? So just think like that. Say if that numerator and denominators are equal, then it means that my null model and my full model are behaving in the same way. In that time, my R-square will be 0 because my model is not doing anything extra to predict that. Right? So if this value becomes close to 0, which means my null model, my whole model is doing well compared to my null model, then my R-square will be on the higher side. Shall I move?
Sir, I didn't got it.
See, your R-square value for the worst case it is 0. For the very good case it is 1. Right? Now, can you tell with respect to this expression in which situation you will get the R-square value as 0? Just forget about what is this NLL mod, what is that NLL null and all those things. This expression when will give the value as 0?
So when the fractions
NLL mod and NLL null are same.
This whole part, if this whole part becomes 1, then only your R-square value will become 0, right? Are you agreeing this?
Yeah.
So now decode it further. At which situation this part will become 1?
Both are same.
When both are same. Which means my null model is my poor model, which is actually not at all using any input to predict my output. It's just using my constant. It's just using my intercept to predict the output. So that is a worst model. Now my whole model is also behaving same as my null model, which means both this and this are same. In that scenario only you will get 1. So which means that is the worst situation. So you will get the R-square as 0. You got the point? The first one?
Yes.
Who raised this?
Yeah, sir, I got it. But how we generate this NLL null model?
No, NNL null model, how will you generate? Say now we have say we have the equation. What is that probability equation? E to the power of z divided by 1 plus e to the power of z. What is that e to the power of z?
E power b1 x plus beta naught.
So b1 x1 plus b naught divided by 1 plus e to the power of b1 x plus b naught. So this is the full model, provided that there is only one input in my data. If you want null model, the null model equation is e to the power of b naught, the whole divided by 1 plus e to the power of b naught. This is the equation for your null model. With respect to this, it's compute the probability. Based upon this probability, it will tell whether it belongs to class 1 or class 2 or class 0 or class 1. So this model, which I'm constructing using both x1 and b naught, it's giving some output, say O1. This model is giving, say, some output O2. If O1 is same as that of O2, both these outputs are same for all the observation, then my model is a useless model. Got this now? Still you have doubt?
I mean, these expressions I'm not able to relate. I mean, how we are calculating and then equating.
See, you don't have any idea about how this e to the power of z divided by 1 plus e to the power of z came?
Yeah, we read that previous to this. Yeah.
Right. So now say you have some data, say 10 observation that you are having. That 10 observation you are substituting in this equation, you will get 10 probability, right?
Mm-hmm.
Yes or no?
Yeah.
For the 10 probability, once you have 10 probability values and the corresponding correct output, can you calculate negative log likelihood?
Yes, sir.
We have discussed, no, even in the quiz I have given that. I have actual output and I have its corresponding probability. You can calculate negative log likelihood, right?
Yeah, yes, sir.
Yes, sir. So now this probability value I'm getting using this equation. With respect to that, I'm just calculating the negative likelihood. Similarly, I'm getting another set of probability using this equation, which is nothing but the intercept model. For that also I can calculate NLL. If both those NLL are same, then that is a poor model, for which the R square is 0.
And how this is coming, the second one?
Second one means?
This e to the power b0 by 1 plus e to the power.
What is intercept in linear regression? What is intercept in linear regression? See, this is the linear regression model. Intercept only model in the sense we are constructing the model only with b naught. All the other inputs are 0. That is what intercept model, right? In
Yes,
this expression, if you substitute in place of x1, if you substitute as 0, this is the equation, right?
Mm-hmm. Yes, sir.
So that is what null model. That is what null model. The null model is nothing but intercept only model.
Yeah, got it.
Right.
Mm-hmm.
Fine. But generally, even though we have spent around 10 minutes to discuss this R square for logistic regression, no one really actually used this McFadden R square to infer the quality of the model. It is debatable. That is the reason in literature also you can see lot of version of the pseudo R square. So the pseudo R square really you can't use to infer anything greatly. Right. So in that sense, we are not actually focused more on, that is, we are not, whenever we build the model, we are actually measuring the performance of the model with respect to the other measure, not really with respect to the McFadden R square. But anyway, as this is a linear model, as we discussed R square for an linear regression, here also there is one kind of R square measure is there, and also it has been proven. There is one article, one research paper is also there. It has been proven, like, even for a good model, even for a very good model, you can't expect this R square value towards 1. So they are proving that around 0.4 and 0.6 only we will be getting, because that log likelihood values and all, say 0.9 is a good prediction. With respect to class 1, 0.9 is a good prediction. But even if you multiply 0.9 and 0.9, and your log likelihood will be further reduced, no? So in that sense, only if it is a very perfect probability, the probability value also, if you are getting only 1 and 0, then only you will be getting that R square value anything close to 1. Otherwise, the R square value will be on some kind of lower side also, lower side only. So it has been proven that anything between 0.4 to 0.6 or 0.4 to 0.7 itself, it's a indicator that it's a very good model, right? You can't expect anything more than 0.7 in terms of McFadden R square. So this is about McFadden R square. Let me go to our workout. So here we have got that McFadden pseudo R square, and this is your log likelihood value. Say if so, here we are getting minus 77, and also that null model is minus 219. And if you see the LLRP value, that LLRP value we are getting as 0, right? So 9.13 into e to the power minus 58, which means it is actually 0. So this is actually, if this LLRP value is anything greater than 0.05, this LLRP value you have to understand in the same way that we will understand the F statistics P value. How we will understand the F statistics P value? Can anyone tell?
This ANOVA table.
Critical value less than 0.05.
Sorry?
Critical value is less than 0.05, we reject the null hypothesis. So it should be 0.05.
Yeah, in simplistic word, I can tell that if it is greater than 0.05, then that model is an useless model. That model is a null model. Yes or no?
So is it the same concept here also?
Yes. So if the p value, this LLR p value, ratio p value is anything greater than 0.05, then it is a null model. Your model is not actually behaving better than your null model. So that model is a kind of useless model.
Useless model.
So
Sir,
we are.
Sir, there in regressions we have a ANOVA table and we take the F statistics p value. What is the table here?
So I'm not exactly sure about this. So how, whether they are using ANOVA, but of course they are using the ANOVA only. ANOVA distribution only, I think they are using here too. But anyway, I'm not sure about it. You can do it. Otherwise, I will refer it. I will tell you what is the kind of exact statistics that they are applying under which I'm not sure about it. But statement is very clear. This p value is anything greater than 0.05, and it is an null model. If it is anything less than 0.05, then we can say that my model is doing something more than my null model, so I can go ahead with this model.
Yeah, sure.
Right. Then again, this is same thing here. The same t statistics only they are using to just evaluate our model significance for each and every variable, whether the each and every variable in my model is significant or not. That they are computing with that same measure that we used to discuss in our linear regression. So this is the coefficient. This is B0, B1, B2. And this is the standard error, how much error incorporated with this, and that t-test coefficient, and that probability of that. So all those things it's printed here. So again, the inferences remain same. Whenever this p-value is greater than 0.05, then that particular variable may not be significant. So whenever the p-value is less than 0.05, that variables are significant. Whenever the p-value is greater than 0.05, that variables are not significant. Right? So but we can't dig deep in terms of statistics as we did it for our linear regression, because in linear regression the output is continuous, but here that output is a kind of a categorical column. So we are not going to really use this stat package of Logit in a deep way, because the main reason why we have used the stat package more in our linear regression is we have to check a lot of assumptions. In order to check all those assumptions like autocorrelation and other things, we need to have some kind of statistical report to comment about the autocorrelation. We need Durbin-Watson. To even comment about the multicollinearity, we need a condition number. To comment about the normality, we can also use some kind of statistical result which has been displayed in that OLS report itself. So in that sense, we have focused more on the statistical report. But here, with respect to the logistic regression, we don't need to check any of those assumptions apart from the multicollinearity. So we can straight away use the sklearn. But anyway, just to tell something about this pseudo R square. And also how to understand the significance of your overall model, and how to understand the significance of each and every feature, we can use this statistical package Logit. So now, by seeing this p-values for each and every variable, we are seeing like fine few features are having the p-value more than 0.05. How can we handle it? The features are having p-value more than 0.05. How can we handle it? How can we handle it?
We will remove those.
Move one by one.
We can drop.
So what that algorithm name?
Yeah, back
RF
or feed forward and backward elimination.
recursive function.
Recursive.
So with respect to the p-value, one by one, if you want to remove, we have to apply backward elimination strategy. So before applying backward elimination strategy, quickly, okay, first we will apply backward elimination strategy, then we will infer the coefficient. So once again, backward elimination strategy, I don't want to type that whole part. So what I can do is, I can copy paste this even in your chat window, because we have done this already. So use this syntax. But of course, I have used something called xtrain1 here. So just include one line here, xtrain1, which is equal to xtrain.copyof. Right? Because after removing some variable from xtrain, if I once again I want those variable, I have to split my data once again from my original data. So what I do is I just kept my xtrain copy.
Sir, you are using xtrain also in line number 3.
You just change this as xtrain1. But anyway, I'm not, while I'm dropping the column, which variable I'm using, that is important. While I'm dropping this column, xtrain1 only I use, no, fine. So anyway, change xtrain1 in that input C column also, and just run it. So anyway, I have changed a couple of things.
Sir, one more thing. In the model, you are using xtrain, not input C.
Yeah, this is the issue. If I copy paste it, if you type it, then it is fine. So what I can do, xtrain C or xtrain1C, I can here use xtrain1C. Is it everything perfect now?
Yeah, I think.
Right. So of course, with respect to the variable names, we have to do some kind of modifications. Now run this and tell me about the significant variables. How many variables now is coming as significant? GRE score, university rating, LOR, CGPA. Only 4 variables now I am getting. What about you people? Is everyone of you getting that 4 variables only?
Yes, sir.
Yes, sir.
So after dropping one by one, so we are ended up with GRE score, university rating, LOR, CGPA. These are all the variables which is still having the p-value less than 0.05 after applying the backward elimination strategy by removing the IP value features one by one. So now, with respect to this feature, I have to construct the model. But anyway, that model is here, right? So that mod res at each and every iteration, I'm just computing this model, building that model. So mod res dot summary of mod res of summary of. So Now you can see all the p values are less than 0.05. So now with respect to the significant model, can you just tell me one-liner statement to explain the relationship between each and every input variable and the output? How can I make this statement with respect to the GRE score 0.9266?
So CGP is a more significant, more important feature to get the
How you are
admission.
telling it is no important?
More, because the 2.8. So CGP should be CGPA should be more to get the admission compared to GRE score. CGPA is very important.
Yeah, that's fine. But give me one statement with respect to GRE score. Morning I told no with respect to beta. How to explain?
Exponential of the beta.
1 unit. 1 unit increase in GRE score, keeping all the things constant.
Can increase the odds of the odd ratio by
by 0.92.
So now say if I write one statement like this, say 1 unit increase in GRE score will increase the what? Will increase the
log of odds ratio.
Admission.
Log of odds ratio.
Odd or
Log of odds ratio.
log of odd will increase the log of odd. Log of odd only we can consider this logit, right? Will increase the logit by
0.9.
Will increase the logit by 0.9266.
Sir, why we are saying logit? Because from the logit we have calculated exponential, right?
Just a minute.
Logit is the logs of odd ratio.
It's odd ratio only, right?
No, log of odds
Let me
ratio.
explain that. By keeping all the other inputs constant. Right? Now I made this statement. Now your doubt is why it is logit. It should be odd. So if you see our explanation, say we have one, say at last we have ended up with this equation p divided by 1 minus p, which is equal to exponential of z. Do you remember this?
Yeah.
Morning we have solved this. P divided by 1 minus p, which is equal to exponential of z. The another equation that we have solved from, that we have derived from this is log of or ln of p divided by 1 minus p is equal to z. Is equal to z. So now what is z? B1 plus B0, provided that it is a simple model. Right. So if you are directly explaining the change in x1 with respect to just B1, here what I have used 0.9266. What is 0.9266? What is 0.9266? It is just some coefficient value. I'm just using this B value as it is to explain my model. So if I'm doing like that, then I have to explain my model with respect to log of p divided by 1 minus p only. That is the reason why I have used logit here.
Okay, got it, sir. I thought you have taken exponential of it. Okay.
No, I have not taken the exponential of it. I have used it alone.
Got it.
Right. So now if you want to say similarly, I am asking you, I requesting you people to write the statement for all the variables. Now what I'm doing is, now I'm just taking, what is my model name? My final model name? Mod underscore risk. Mod underscore risk dot params. So it actually giving me only the coefficients, right? Yes or no? What these values are? What these values are?
Coefficients.
Coefficients. Now I'm just taking the NP dot exponential of it. Right? I'm taking the NP dot exponential. Once I take the NP dot exponential, the GRE score now it's coming as 2.52. Now how can I write this statement? Now how can I write this statement with respect to GRE score? One unit increase in GRE score will increase the odd of, even with a proper statement, odd of getting admission by 2.52 times by keeping all other inputs constant. By keeping all other inputs constant. Everyone getting this? Why here I am writing in terms of odd with respect to the value 2.52, whereas previously I have speak in terms of logit with a value 0.96. Any doubt in this?
Yeah, sir. Let's suppose coefficient is negative, the exponential will make it positive, right?
Yes.
So while interpreting, are we going to say decrease or we just say increase always?
No, decrease.
So I mean the increase or decrease will use based on sign.
See, in that sense, what you have to tell is you have to explain that with respect to the other parameter. If you say if it is coming in negative, then it means that say
rejection of admission.
It is actually the rejection measure. Now we are speaking in terms of the admission. What is the chance that he will get admit, right? So if it is comes in negative, you have to speak with that coefficient with the respect to the rejection rate.
Okay.
1 unit increase in GRE score will increase the odd of getting rejected by that many times.
Okay.
Right. So this is this is how you need to infer the coefficients. So by seeing that CGPA is having a very high value 14.8. So for every 1 unit increase in CGPA, the chance for getting admission, the odd of not chance, the odd of getting admission is increased by 14.82 times. So CGPA is actually having the major factor in getting the admission in the institute. So this explainability is really matters, especially while you are doing the logistic regression. Because for this explainability only, we are really going for logistic regression. If this explainability is not matter, only the predictive ability is matter. I'm concentrating on, my focus will be on how accurately I'm predicting, not the explainability. Then you can go with some other models rather than doing this stuff with the logistic regression model. So as logistic regression model is a linear model, it won't actually produce very great performance compared to your nonlinear model. But this explainability, it is very straightforward and very linear with respect to the logistic regression model, whereas that explainability that we are going to do in our coming session with respect to the decision tree and random forest are not very linear. That is, not very linear means for each and every observation that explainability may not remain same. But here with respect to the logistic regression model, for each and every observation, the explainability that we are doing may remain same. So that is the greater advantage of using this logistic regression.
Sir, I have a doubt. So CGPA odds ratio is 14.82, right? That means P by 1 minus P equal to 14.8.
Sorry?
That means what is that P by 1 minus P equal to 14, right? So that is a probability. So then what is the probability of getting chance of admission?
See,
So
that ratio is it is P divided by 1 minus P. So
P
what
equal to 14, yeah, 14 by 1.
No, you can't tell us. Yeah, for every 14 times you are rolling something, only one time you have that chance of getting.
Yeah, that means in the 14, if there are 14 people, maybe I'll get the chance.
No, you can't think like that with 14 people. So 14, say there is compared to other feature, this CGPA, for every 1 unit increase in CGPA, along with that you have to relate this odd off.
Yeah, that's how I'm writing. So P by 1 minus P equal to 14.
Yeah, if CGPA is increased one unit, then 14 times you will get an 14 times more chance you have compared to not getting selected in that particular institute.
Yeah.
Right. So it is with respect to 1 unit in CGPA. What is this odd of getting chance? Not for total amount of people and other things.
Yeah, got it.
Sir, can we conclude CGPA is playing more role in the admission?
Yes, exactly.
Okay.
Yeah, Joseph, that coefficients won't change actually. You just try that. We are taking again and again. I think the coefficient inference may not change. That proportionality will be remain same.
Okay, sir, I will try that.
Yeah, you please try that and let me know. As we are taking P divided by 1 minus P internally, so that scaled function, I think, will normalize it, and that proportionality will get cancelled out. So we may get this same coefficient only. But anyway, I will also check that. But in terms of predictive ability, there will be no change. Definitely, there will be no change. So the predictive ability will remain same. And also in terms of coefficient, we can't expect any change as we are doing P divided by 1 minus P. Log of P divided by 1 minus P, that P value and P minus 1 value that we are getting through that different functions about. So obviously that proportionality will remain same whether we are scaling or not. So we will get the same coefficient only. But anyway, you just please cross verify it. So this is about the inference part. So I will conclude my session just by implementing the same thing with respect to the logistic regression, so that in next class we will be doing with computing all the metrics. So today we don't have the time to compute all those metrics. We'll be starting to compute, analyze all those metrics in our next session. But before that, how to implement the same logistic regression with sklearn package, that alone we will be doing now. So from sklearn dot linear model, import logistic regression. And I'm just keeping something as mod log. Logistic regression of the same way as we used linear regression. Mod dot sit of our X train Y train. If you want to predict, ypred equal to mod underscore log predict of your X test. Right. So in terms of implementing this in sklearn, it's not at all difficult. So just like that, calling that logistic regression from linear model and defining that as an empty object and fitting our data into it and predicting it with the test part will actually directly give you the ypred value. So can you think of how it is computing this ypred? Basically, logistic regression output is some probability value, right? So how it is computing this ypred?
Based on the by default 0.5 correlation.
By default 0.5.
Threshold.
If you want to see that, rather than putting this as predict, there is one another function like predict proba. Predict proba of X test. So this is its corresponding probability value. This is its corresponding probability value. So why it's the probability value displaying in two columns?
One is 0 and one is for 1.
One is for 0 and one is for 1. So let me just round off this. Can you compare that ypred output with this predict proba output?
Second series
in reverse case.
See, the predict proba function in sklearn will give you two probability. The first column probability is talking about the 0 class. If the first observation belongs to 0 class, what is its probability? If the first observation belongs to 1 class, what is its probability? Of course, if you add these two things, you will get 1. If you add these two things, you will get 1. Now, for the first observation, which column probability is high? 0 column probability is high or 1 column probability is high?
0.
0 column, which means with 93% confidence, with 93% of probability, it is saying that the first observation in your test data belongs to class 0. That is the reason why ypred value is 0 here. What about the second observation? For the second observation, which column value is high?
1.
So first column value, with 20% probability, it's saying that it belongs to class 0. With 80% probability, it's saying that it belongs to class 1. So it is 1. So by default, it is using the 0.5 as a threshold. So if out of these two columns, in which column the probability value is greater than 0.5, that corresponding class has been assigned to that particular observation. So like that, it is actually printing all the ypred values. But if you want to see the probability, you can use the predict proba. So in our next session, we will be using this predict proba, threshold, and all those things in a deep way to improve our model performance. But before improving our model performance, we have to first study in what are all the different ways through which I can compute the model performance. So in our next class, we are going to discuss about all those metrics: accuracy score, recall, precision, F1 score, sensitivity, specificity, all those things, ROC curve, all those things we are going to discuss. Then once we have that ability of computing all those measures and understanding the model with respect to all those measures, how to improve that model performance by adjusting this threshold rather than keeping that 0.5 as a threshold. How can I play with the threshold so that I can improve the model performance? All those things we are going to study in our next session. If you have any doubt with respect to what we discussed in today's session, you can ask me now.
Here 0.934 is towards the admission, right? Chance of getting admission.
No.
Not getting admission.
Not
Say,
get.
not getting admission. Say generally one probability. What if only one probability? Say we have find only one expression for p, right? During our mathematical workout. What is that expression? P equal to e to the power of z divided by 1 plus e to the power of z. If you are computing only one probability using that equation, then that particular probability is talking about the probability of getting admission. But here, this predict proba function in sklearn have that extra ability to compute that probability for both classes. What is the probability for 0 class and what is the probability for 1 class? So the first column of information throughout for all the observation will tells what is the probability that this particular observation belongs to class 0. Whereas the second column of this array will tell that what is the probability that it belongs to class class 1. So this is class 0 probability. The first column is class 0 probability. The second column is class 1 probability.
Yeah. Thank you.
So if you add it, say 0.934 plus 0.006 what? 1, right?
Yes.
So which means out of total chance, what is the chance that it belongs to class belongs to 0 and what is the chance it belongs to class 1? That actually it's splitting and giving to us. Any other doubt?
Fine, sir. We'll ask in next class if something comes.
Yeah, sure. So just go through it. If you have any queries with respect to whatever the things that we have discussed, you can even ask in our tomorrow session. Yeah. I think someone about to ask something. No?
So maybe when they
Yes.
run it again, if there are any doubts, then.
Sure, sure.
Yeah, somebody was going to ask something, I guess.
No, sir, we will ask tomorrow.
Amit, you wanted to ask something, right?
Who was it, Abhishek?
I think Amit.
Yes, Amit, any doubts, please?
No, I didn't ask.
Okay.
Fine. Anyway, go through it. And if you have any queries for what we have discussed today, you can ask even before starting tomorrow's session. So we can discuss during our next session. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.